The event is being recorded and will be made available on our YouTube site following the conference. So feel free to come back and watch again or share with others if you need to. We have a full agenda today. We'll see how things are going. We may take a 5-minute or 10-minute break midway through just to get everybody a chance to get up and stretch their legs. So I'll keep you posted on that. And finally, we will do our best to stay on time, but we are going to follow a rolling schedule. So we'll just keep working through the day. With that, I think we should just go ahead and dive in and get started. Our first speaker this morning is Nick Lamke. Nick will be talking to us about river-aquifer interactions in the Lewis and Clark Regional Water System Wellfield. Nick works for the Department of Ag and Natural Resources as a geologist in the Geological Survey Program. He works on geologic and hydrologic investigations in Brule County, the Big Sioux Aquifer, and other areas in the state. And today he'll be talking to us about an investigation of river-aquifer interactions in the Missouri River Aquifer, Elk Point Management Unit, south of Vermilion, South Dakota. Nick, are you with us?
Yep, I'm with you.
All right. You want to share your screen?
Yeah.
All right, we're seeing it.
All right, great. Okay, so I'm going to talk about how to use numerical models to simulate river-aquifer interactions. And the site that I was working on is the Lewis and Clark Regional Water System Wellfield. So the site's located south of Vermilion, South Dakota. There are 11 production wells located along the Missouri River in these orange boxes. And we have the Vermilion River to the northeast, and obviously the Missouri River to the southwest. And this black line is the AOI, or the model domain. And over here we have, this is an extension of the Missouri Aquifer, but I ended the boundary right here just to have an end to the model domain. And so there were 8 monitoring wells scattered throughout the aquifer, and hydraulic heads were measured in all of those, which were very helpful for the numerical model. So that's the site location. So the reason that we did this project was to look at the river-aquifer interaction. And so streams can interact with the river in 3 basic ways. You can have a gaining stream, a losing stream, or you can have both, where some reaches of the river are gaining or losing. And in this location, the Missouri Aquifer has a strong hydraulic connection with the river and can gain or lose water depending on the elevation of the river stage and the water table. So since the production wells are located directly adjacent to the stream, you get conditions where you lower the water table elevation near the stream, which induces flow from the stream into the river. And so the purpose of this model was to look at quantifying this flow into the well from the river. And the reason you want to use a numerical model to do this is because it's impractical and very difficult to go out into the field and actually measure that. So the best way to do it is to make a numerical model. So this is the general workflow on how to set up a numerical model. So usually just you start off with a question or define the purpose of the model. And then you have to build a conceptual model, which is basically just a series of all available information about the site. Then you need to pick a modeling code to use to simulate flow. And then you have to build the numerical model and design it. And then you go through a calibration process and reject or accept a calibration and go back and adjust things if you need to as necessary. So I'm going to talk about kind of each of these steps for the rest of the PowerPoint to give you an idea of how I put this together. So in the conceptual model, I had so I already had a report that had was a previous study the SDSU used in 2015. From February through September 2015. And in that report, they monitored water levels, Missouri River stage. They had some measured values for hydraulic conductivity and pumping data for all the production wells, and which is basically all the information you need to put together a good numerical flow model. And the general conclusions of that report were that pumping the 11 production wells didn't influence the aquifer beyond 0.4 miles from the well field. So already knew that the connection between the river and the aquifer was there and pretty strong. So the next step sort of is to define your sources and sinks for the model area. So there's three main ones for this area, which is aerial recharge and the Vermilion River to the northeast and the Missouri River to the southwest. So when I was designing the model, I noticed that there were this backwater over in here, and in these areas where the water is slower and it allows for finer sediments to deposit, which lowers the vertical hydraulic conductivity of the river there. So the hydraulic connection is slower. There's less flow rate there in that area. So that's why I broke up the Missouri River into three segments and defined different, the parameter that the model sees is called conductance. So I defined three different conductances for those three segments. And then to the northwest, there is flow in reality going back and forth through here. And I simulated this in a couple different ways, but I found that didn't really have an impact. It's far enough away from the area of interest down here that it didn't really have an impact on what was happening at the well field. So I left this as a no flow boundary is what it's called. So it did nothing during the model domain or during the simulations. And the next step is to define the aquifer geometry. So this is an isopack map showing the aquifer thickness. And there's some key features that I noticed when I put this together. Is we have a bedrock high sort of in the center part of the aquifer. And the aquifer sort of thins towards the south and southeast as it approaches the river. This is mainly just because it's mainly driven by the surface elevation. So it kind of drops off as it approaches the river there and turns into a sandbar. And that the well field is located in a region of the aquifer that's fairly thick. So most of the aquifer is about 100 feet thick. And the base of the aquifer is bedrock. So basically an impermeable surface there. But in this area, in the production well field, the aquifer was about 125 feet thick. So was a thick region of the aquifer. So there's a lot of room for water to move around in the well field. So then I looked at some precipitation data and the river stage data. So what you end up having, what I ended up doing was kind of making an assessment of the total max and min. So really the river stage didn't change all that much throughout the period of record that the study from the report that I was basing this off of was. So from March to September. So the river stage only varied about a foot throughout that whole thing. And one of the things you have to consider when you're making a model is computation times. So, and you have to make a few assumptions to simplify things. And one of the assumptions I made was that just from an assessment of this, I noticed that the river stage in July was relatively stable. It didn't change a whole lot. So that was one parameter I didn't have to vary when I was calibrating the model. And the precipitation was relatively high, which was good for me to make the assumption that the irrigation wells in the area probably weren't pumping a whole lot and having a big impact on hydraulic heads during this time period. And it also provides a conservative estimate. So area recharge would have been relatively high. So most of the flow so the aquifer was full from aerial recharge. So any flow from the river would be minimized. So I use data, precipitation, and stream stage data from July to August to calibrate the model. And some more data that I fed into the model. These are the hydraulic heads that were measured in the monitoring wells. And basically, they remained stable throughout that duration of the month. There wasn't a whole lot of variation, except for in wells 2015, 06, 07, and 09, which are wells that are located right next to production wells. So you can kind of see when pumping rates get really low, the water levels in those wells sort of goes back up. When pumping rates get jacked back up, water levels go back down. But even so, the amount that they go up and down is still pretty small. So, you know, things stabilize pretty quickly, which means that there's a good connection with the river also. And this was probably the most helpful piece of information that I had, which are measured hydraulic conductivity values from other studies done from aquifer tests. So this is really helpful because it helps me. Hydraulic conductivity is one of those variables like recharge where you just never know what it's going to be. And it's really everything is pretty heterogeneous enough that you just can't know it that well. But in this case, we knew it pretty well. So these numbers from about 172 to 699 were our min and max. And these numbers are within the range of well-sorted sands and glacial outwash. So, which is exactly what we have. So that's good. We know we're in the realm of reality there. So putting all this conceptual model data together to make the numerical model, you make a series of decisions. So you have to select the code, and there are many versions of ModFlow out there. So I chose ModFlow 2005, which at the time I made this model was the newest version available. And then there are a lot of different programs to use as a pre and post processor for ModFlow out there. And I used GMS by Aquavio, which is a nice program that allows you to take a GIS conceptual model approach to assigning values to the grid and ModFlow. And for calibration, I used a software and analytical code called Pfas, which is a parameter estimation, an automated parameter estimation code. And to develop the capture zones, I used a program called ModPath, and which creates particle tracks that kind of look like little spider webs that flow perpendicular to the your hydraulic head contours. And then I used a program called ZoneBudget to calculate water budgets, and ModFlow calculates an overall water budget for your entire model. But because I was looking at specific regions, I needed something that calculated a sub-regional water budget, which ZoneBudget does. So that was nice. And then after you go through this whole workflow, at the end of it, I can calculate the river inflow per capture zone. So this is what the numerical model looks like once it's put together. And we're looking at the grid shell with the colored areas, the pink and the yellow and the red are cells in the model that were designated a source or a sink. So the purple cells are the Missouri River. So that's how the model sees the Missouri River. And then on the other side is the Vermilion River. And the red lines in the middle of the model and along here are observation wells and production wells. And these are the cells in the model that you apply changing variables to. So this is where the conductance goes, the river stage, and all of that. Aerial recharge is applied uniformly across the whole top of the model. And that is what the model looks like. So I don't think I mentioned, but you can see, so you can see some of those features from that ISOPAC map. So right in here, you can see the bedrock high, and you can see the deeper portions of the aquifer where the well field is. So it's a good way to capture, numerical models are a good way to capture the geometry of an aquifer. So that's what the numerical model looks like. From a 2D point of view, I broke the model down into 2 layers to sort of get a three-dimensional, to get a more of a 3D solution. And we're looking at the well field from the southern end looking north. So all the wells are in space facing to the north there. But what I wanted to show is just this deeper portion of the aquifer and just sort of a 2D look of how the model captures geometry. So the colors you're looking at are the elevations assigned to each cell. So ModFlow sees a bottom elevation and a top elevation of each cell. And that's how it knows what hydraulic heads are and what all the other elevation data can do inside the model domain. So once you have everything put together and the geometry is right and the structure of the model is okay, you can run it. And this is what ModFlow outputs. So this is just a hydraulic head map showing the contours over time. So I ran the model for 31 days in July, and you can just see the variable pumping rates, the cone of depressions around the wells. And one interesting feature is we have a groundwater divide sort of right over here to the east of the well field. So all the water flows, all the water. So if there's a line right here, all the water on this side of it flows this way, and all the water on this side of it flows that way. So you can really just see the cone of depression where all the wells are pumping. So once you have this solution, you can start running other codes like ModPath. And so this is what the capture zones look like in 3 dimensions. So I just kind of wanted to, so capture zones are 3-dimensional regions of an aquifer that supply recharge to a well. And ModFlow calculates these, they're called path lines, based on the average linear velocity, which is just it has units of length per time, and it knows how fast the water is moving based on the porosity and the hydraulic gradient. And you set a time for how long to track the particles, and the particles will either terminate once the time is up, or they'll keep going until it runs for enough time, they'll terminate at the nearest source or sink. So in this case, they quickly terminated at the Missouri River as a source in less than 31 days. And this is the 2D view of those capture zones and particle tracks. So so what I ended up doing was lumping the capture zones into 6 different zones for zone budget, and which calculates a water budget just for this zone within these boundaries. So it calculates the flow coming in from this way and the flow coming in from the river and aerial recharge and all the other sources and sinks just for this little region. And when you break down the numbers, I ended up seeing 69% up here, 82%, 80. So basically 61 to 82% river contribution inflow into each of these capture zones when wells are pumping. So the total average contribution from river inflow to the well field is about 76%. So lots of river water flowing into the well field and recharging those wells. Another way to think about this and look at what the model is doing behind the scenes is to plot the values I use to calculate those previous numbers in that figure over time throughout the duration of the model run. So the dashed lines are well discharge, and the bottom solid lines are the river inflow into each of those zones that I was talking about. I grouped these into 3 different groups based on the well discharge groups, but you can see the relationship between well discharge and river inflow. So as you would expect, the harder you pump a well induces a response in river inflow. So harder you pump a well, the more river inflow there is. And this is what you would expect. So that is good that the model is simulating that just fine. And another way you can look at this is to see this is showing the actual grid of the model, and the cells that have cooler colors in them are the ones that are contributing the most flow into the well fields from the river. So you can see that when you develop these capture zones, and it intersects a portion of the Missouri River here and calculates the flow from these cells into that zone. So that's kind of what's happening behind the scenes there. So it's just taking us a slice of the model and calculating the flow between all the cells in that zone. So with that, I had some conclusions, some next steps. So I thought this was a really good example to leverage existing data to gain some deeper insights into how an aquifer system behaves. So it was really nice to use data that was already collected to make a numerical model. And on average, 76% of the water flowing to the production wells was induced flow from the Missouri River. And some things I'm doing now are running a new suite of simulations that have much longer run times, and they vary other variables like river stage and pumping rates to see how much the flow would vary in more extreme conditions, so we can get a maximum and minimum value. So that's all I have.
Great. Thank you, Nick. We do have a couple of questions. First ones, are there any plans to conduct additional drilling to confirm any of the predictions of the model?
There are no plans in the works for the SDGS to conduct any additional drilling, but the Lewis and Clark is installing new production wells there. So I've seen some of the results from the holes they drilled for that. So no, there is no future plans to do more drilling at the moment.
Are you able to work some of the data from those new wells into your model at some point?
Yeah, that's the great thing about these numerical models, is that they're dynamic. Any new information that I get can be incorporated into the existing model, and you can see the results of adding new wells or varying any other variable you'd like to see, and see how it changes. So I don't expect that 76% number would change a whole lot. It's more about the location of the wells. So the further into the aquifer you go, the longer it takes for water to be induced from the river. So it would initially use more water from further in from the aquifer to get going, and it would use less river water initially, but that 76% number probably isn't going to change much.
Another question with drought and potential for lower river levels, can you use the model to help evaluate potential impacts from lower flows in the river and things like that?
Yes, definitely. And that's one of the things I'm looking at right now, is if river stages get dramatically lower, like they are right now, what does that mean for wells that are located along them?
Sorry, a lot of questions for me, apologize, but I'm curious, can you describe a little bit how those production wells are installed? Are they just vertical wells next to the river, or?
Yeah, most of them are vertical. I think all the ones that are running right now are vertical wells. And initially they had some horizontal wells that drilled into those, but for one reason or another, they didn't work out. mechanically, I guess. So yeah, most of them are vertical wells. The new wells that are going in are they're rainy collection wells. So they have it's basically a giant cylinder that drilled down to bedrock, and they run horizontal pipes underneath the river and into the aquifer that get that gravity feed that cylinder, and they pump water out of those. So
Excellent. Thank you for that. Well, I don't see any other questions popping up. So Nick, we appreciate you taking the time to be here with us this morning and giving us your insight. Thank you so much.
great. Thank you.
All right. Tanner, are you with us?
Yes, I am.
All right. So we're going to move on. Our next speaker this morning is Tanner Clausen, who will discuss DANR's Riparian Buffer Initiative. Tanner is an environmental scientist with DANR in the Sioux Falls office and has worked in the Watershed Protection Program for 3 years. Tanner graduated from Redfield High School and continued his education at SDSU in Brookings, where he received a Bachelor's of Science degree in Wildlife and Fisheries Science in 2016. Tanner is married to his wife, Sydney, and together they live outside of Key, South Dakota. Tanner joins us today to tell us about the Riparian Buffer Initiative and the benefits of enrolling in the program that is currently underway across South Dakota. All right, Tanner, it's all yours.
Well, thank you, Brian.
Did you want to share your screen or?
Yep, I'm working on it right now.
Awesome.
Let's see, it's a little bit different than Teams here.
Right, they have to make every platform just a little bit different.
Yeah, I see that. Where is the, oh, here we go. See it lit up in green here. Okay. You see it now?
Not yet. Maybe it's working its way through cyberspace here. There, it's coming. All right, we're seeing the edit mode. There you go. You're all set.
Okay, awesome. So as Brian stated, I'm going to talk about the Riparian Buffer Initiative, also known as RBI. And first, I'd like to start with discussing the before and after picture, or the before and after pictures here on the first slide. So this producer had previously grazed this pasture with cattle, and he was using the stream, which in this case is actually Skunk Creek, as his primary water source. And if you don't know much about cattle, if they're given the opportunity, they will spend the majority of the time in the riparian area. And that tends to beat it up pretty bad. As you can see here in that picture on the left, there's dirt showing in spots. Granted, the water is a little bit low, but the grass that's there's not much grass. It's pretty thin. That's not going to work as a very good buffer for keeping anything out of the stream that could potentially run into it. But this producer decided to enroll this pasture into a riparian buffer program with the Big Sioux River project. And a few years after it was enrolled, the picture on the right was taken. As you can see there, the grass has grown back substantially more than there was in the left picture. And that's going to work as a lot better buffer for slowing down any runoff or pollutants that might run into the water. And not only that, but we also have vegetation within the stream. So if stuff does, like nutrients, say we have nitrates coming down, those plants can also hang on, try to grab onto that, use it as plant uptake, and filter some of that stuff out of the stream as well. So this is just a prime example of how buffers are extremely effective in achieving water quality that we strive for. To qualify for RBI, the water body must be found on the ARSD 745103 list, or be designated by a local board of county commissioners. And the ARSD 745103 list is just a list of water bodies that have designated beneficial uses in the state of South Dakota. The county commissioners portion of that might be a little confusing. So I guess the best way to explain that is, if the water body isn't on the 745103 list, the local board of county commissioners in whichever county can vote to approve to to make the water body included in the property tax, which is a 50% tax relief, as well as qualify for the RBI project. So there's really two avenues to be able to qualify a specific stream for RBI. The buffer must be a minimum of 50 feet, not to exceed 120 feet wide. And we chose that maximum of 120 feet because at that distance, 90% of the pollutant load is reduced. The landowner must have existing perennial vegetation. And if there's not perennial vegetation, he or she must be willing to establish perennial vegetation, because in order to have a properly functioning buffer, there must be vegetation there year round. The vegetation may be grazed or may not be grazed between May 1st and September 30th, because that is during the recreational season. So there's kids swimming, people boating, kayaking, wading. There's just a lot of people out and about during obviously our summer months and using the water bodies throughout South Dakota. So we're going to defer the grazing from that period. The vegetation may not be hayed or mowed between May 1st and August 1st. And that is so nesting birds have the opportunity to use this buffer to hatch and raise their clutch. And there must be a minimum of 4 inches of vegetation at all times. This essentially is just for the health of the buffer, because if there's much less than 4 inches, if you think about your yard, the water can run off extremely fast if you get a couple inch rainfall. So it doesn't have a very big window to slow that runoff down if there's nothing there to catch it or slow it down. So we're trying to prevent erosion. And that 4 inch minimum is also keeping the landowner from overutilizing that ground, because the payment is to set that land aside for water quality and wildlife habitat. So for us to get a benefit out of it, there has to be at least some residual vegetation there. And these acres will be enrolled into the program, the RBI program, for 10 years. And the contract will be held between the state and the landowner. So there are many benefits, water quality and wildlife benefits, to install a buffer. Buffers help slow down runoff, which can reduce the intensity and frequency of flood events. They also help filter out pollutants such as nutrients, sediments, animal waste, and chemicals. And they do this by the vegetation within the buffer can remove these pollutants from the runoff using plant uptake. So like I was explaining with the yard scenario before, so if you have a pasture, which say there's 6, 8, 10 inches of vegetation there, there's more resistance for that water as it's going through this vegetation. So it's slowing down those particles, they're filtering out within that buffer, and then those plants can use the nutrients. We'll just use nitrogen and phosphorus, for example. They can use nitrogen and phosphorus to make even more grass. So if you're haying it off, that's actually a bonus. That filter strip or buffer is actually essentially can be fertilizing itself. Riparian buffers also increase bank stabilization, and the vegetation. The best scenario I can give with this is the vegetation above ground reduces the impact of rain and wind events on the soil surface, while the living root below ground is helping hold these soils in place. So the good rule of thumb is they say if there's 6 inches of vegetation above ground, there's roughly 6 inches of roots below ground. So the roots and the vegetation are working in unison to keep that soil in place, which is essentially what we're trying to get to hold these banks in place, which keeps the sediment out of the streams and it keeps a healthy buffer. And these buffers create beneficial terrestrial and aquatic habitat for many species of wildlife. So how do these buffers benefit landowners? Well, with the RBI buffer, vegetation may be hayed or grazed. So the landowners can still use their ground. They're not having to sacrifice these acres and not be able to use them. There's cost share available for alternative water and exclusion fence. This is increasing the infrastructure on the landowner's property, which essentially is increasing the land value. There's increased bank stabilization, as I just explained in the previous slide, but this is keeping the land from eroding and washing away. And once these banks start to wash away and they get to be a cut bank, it's really hard to keep them from continually washing, especially when you get in flood events and you can't control the rain we get. So like 2019 was a pretty bad year for undercutting, and when you go around the outside of rivers and stream bends, that's where it tends to, there's so much pressure with that excess water that it can really undercut these banks, and then you can be losing, say, 5, 10, 20 feet away. We've even seen on the Big Sioux. So that's kind of depressing when you see that all going away, and then it's not good for landowner either, because you're losing land that you initially paid for. So that's a benefit, to keep your bank where it's at. And there's also incentive payments and a 50% tax reduction on the enrolled acres. So next I'll talk about the priority areas. And at this time, the priority area is the entire Big Sioux River Basin. So we have it split here from the upper Big Sioux River Basin and the lower Big Sioux River Basin. And we'll talk about the upper Big Sioux first. It's a little bit easier to read. Zoomed in here, so we have a map obviously on the left, and then a list of the eligible streams there on the right. And all the blue lines are the eligible streams. So I'll just give you guys a minute to look over any streams that you might be interested in. I know it takes a little bit to maybe read through the list of streams and then also see where they're at on the map if you're not familiar. All right, now onto the lower Big Sioux River Basin. It's the same thing here. All the blue lines are the eligible streams, and there's a list of all the eligible streams on the right. And if anybody wants a copy of the eligible streams or a map or even a presentation, I guess you can just get a hold of me, or either Barry, Chris, or I get a hold of one of us, and we can get you whatever info you might be interested in. I'll also give you a minute here to look over these streams as well. All right, so the rental payments for qualified stream segments will be based on 100% of the county CRP rental rate for crop and pasture land. Additionally, pasture land will qualify for exclusion fence and alternative water at 75% cost share, but not to exceed $5,000 per contract. We are offering cost share for exclusion fence and alternative water because ultimately it makes for better grazing management, which directly benefits water quality and wildlife habitat. So the exclusion fence is the fence is the fence that is excluding the cattle or livestock from accessing the riparian area. And as I said before, if cattle especially, if they're given the opportunity, they're going to spend the majority of the time in the riparian area, especially when it gets hot, say the end of June, July, August. They're going to be in the water, wallowing, trying to keep the flies off, trying to stay cool. And that's what they tend to do their business as well. So that's not good for water quality. They tend to really beat the banks up, as you can see in that first picture. So if you're spending all that hoof action, they're spending all that time there. There's not a lot of vegetation that can grow, but the vegetation that does grow there, it's usually constantly eaten down, stays fairly supple because it never gets a chance to head out with all the pressure of the cattle there. So anyway, we want to have that exclusion fence from either that 50-foot mark or the 120-foot mark, keep those cattle out of there. But while doing that, we're also taking that watering source away from those cows. And if that's the only water source that producer has, then they either have to pay for that alternative water, which is obviously an added cost. And we're willing to help pay for that alternative water as well. Because in order to get a landowner to do something that he may or may not be really wanting to do, he might think it's the right thing, but all this infrastructure costs money. So it's their livelihood. So in order to get them to go along with the project and actually see the benefits of it, we're willing to help pay for exclusion fence and alternative water. And alternative water can come in various different forms. It could be a solar pump pumping water from the creek to a tank. It could be a solar pump on a trailer where maybe he's just moving it. He's doing a rotation, wants to do a rotational grazing system, and he's going to move it a couple times. Maybe he'll have it in one spot, and then 200 in a week or two, he'll have it 200 yards downstream, pumping out of there. So he'd be pretty mobile with that. Or if he wanted to, he could haul water if he so chose to do that. Otherwise, there's also rural water hookups, and these tend to be fairly common. So it's the cleanest water that you can get for your cows, and the cattle tend to do or have better daily gains on it. And I say cows just because that's the most common type of livestock we run into with doing these or in these riparian areas. But yeah, those rural water hookups could be just rural water to a tank out in the pasture if you wanted one tank, or it could be do a bunch, trench it in and have a few couplers out there. So you could also do a rotational grazing system. So all this infrastructure can be pretty easy for the landowner to change his management if he wanted to. Kind of like I was saying, where by getting these cattle off of the riparian area where you can't move that water source is stationary. So if you can get that water to a tank and you're moving it around, it actually does make for a better grazing management, and it's better for the health of the whole pasture. So the rental payments will be made in 3 equal payments in years 1, 3, and 5, with the exception if the enrolled acres, if that payment is less than $10,000 or less, the entire payment will be made in year 1. The payments for exclusion fence and alternative water will be made as the practices are installed. The total budget for RBI is $4,005,000, with $3 million coming from House Bill 1256, which was given to us by the South Dakota legislature, $505,000 from the Department of Ag and Natural Resources, and $500,000 from the South Dakota Game Fish and Parks. The American Recovery Plan Act is a funding source given to us by the federal government. We currently have a proposal in for $1 million, and if that proposal is successful, we'll be able to open up RBI statewide, and it'll essentially be just like how we're selling it in the Big Sioux. So in order to qualify, it has to be on the 745103 list or be designated by the county commissioners. And if we do end up spending the entire $1 million, we have the ability to reapply for more funding. So here's a list of all our project partners, and then I went over the financial partners a couple slides ago. But without partnerships, it'd be extremely difficult to run a successful project. So I would like to recognize all our partners by giving you guys a minute to read through this list. So why monitor? We will monitor the RVI projects so we can show results of how riparian buffers perform. We're going to start by using Step L, which Step L is an Excel-based model that we will use to calculate load reductions, such as nitrogen, phosphorus, and sediment on the enrolled acres. We will continue to use existing stream monitoring to track water quality, and we will do periodic field checks to make sure landowners are in compliance. So far, the delivery of RVI has been a combination of the Department of Ag and Natural Resource staff, as well as the Pheasants Forever staff. The Danner staff have handled the presentations, grant applications, landowner workshops, and landowner contacts, while the Pheasants Forever staff has mainly handled landowner contacts. So the landowner contacts for Pheasants Forever normally are the actual out in the field, maybe going to the producer's place or the landowner's place and talking about them with various programs. So with that, that concludes my presentation, and I will answer any questions that you guys may have.
Well, thank you, Tanner. Appreciate that presentation. We did have a question in the chat, but it looks like it's been answered by Barry McClowry from DANR. So thank you, Barry. Did we have any other questions for Tanner this morning? All right. Oh, no, one just popped up. Since the introduction of the buffer, have we seen a decrease in eutrophication?
I don't know the answer to that question. I don't know if Barry or Chris does, if we have that information. So I'm going to defer that question.
Okay.
And I can also get back to him if nobody knows that answer.
Right. And feel free to email or reach out to Tanner if we have questions we need to follow up on. Another one is are the ARPA funds that are made available, how soon would you expect to bring RBI statewide?
Well, once we receive the ARPA funds, or once we find out approval, the groundwork is pretty well laid out to roll it out statewide, since we were, essentially had everything ready to go for our RCPP proposal that we were not successful with. So a lot of that groundwork is already laid out. Pheasants Forever, I've already given a presentation to their staff, so they're aware of the RVI program, and they probably know a little bit about it. Maybe not as well as they would have to for all of the staff, but I would say almost right away. It would almost be able to be sold statewide right away.
Okay. The one additional question was there a previous program out west, or has something changed, or I don't know if that.
No, there was. So we had never opened it up at least with RBI. We had never had it opened up statewide. So the $3 million from House Bill 1256 that was given to us was designated for the Big Sioux River Basin. So we were solely focusing on Big Sioux with that money and with the Danner and GFP money. But we did have aspirations of having a statewide project, so that would be considered out west in the Belfouche area, Belfouche and the Cheyenne River Basin area. But we never got, like I said, our RCPP grant application wasn't successful. So no, there wasn't ever a project being sold, or RBI was never being sold out there.
Brian.
Go ahead, Barry.
Thank you. I think maybe what Mr. McVeigh is referring to is probably there was a statewide effort that was in place for property tax relief with buffers. And I believe that's probably what John was referring to. But as far as this project or the program that Danner has in place here with the Riparian Buffer Initiative, it has not been out west. I think that's probably what John is asking about.
All right, great. Thank you, Barry.
And I guess I think I said it throughout the presentation, but that tax relief was also changed from 40 to 50%. So now it's 50%.
Very good. Well, I don't see any other questions. So Tanner, appreciate it. Thank you for taking the time to be here with us today and give us info on RBI, and we wish it the program great success. We are a bit ahead of schedule, so and I'm out of coffee. So if everybody doesn't mind, I think we're gonna pause until 9:05. It's 8:57 right now. We will pause or pick back up at 9:05. So if folks wanna, take a break or fill their coffee quick, I'll just leave everything up and running and I will reconvene at 9:05. So we'll see you in just a few minutes. All right, welcome back, everyone. Hope you had a chance to fill your coffee up and get ready to go for some more excellent presentations here. Our next speaker is Kevin Eisen. He will provide an introduction to PFAS and provide an update on the existing and rapidly developing PFAS regulations from the EPA and Midwestern states. Kevin is a licensed professional engineer in South Dakota, North Dakota, Montana, Minnesota, Iowa, and Wisconsin, and has over 20 years of experience working at environmental investigation and remediation sites. Kevin's work at Barr has included planning, designing, and managing environmental investigations and remediations at project sites involving soil gas, groundwater, and geochemistry within a range of regulatory programs. Kevin has been closely tracking federal and Midwestern state PFAS activities, rulemaking, and enforcement, and is actively working on multiple PFAS-driven projects. Welcome, Kevin. Take it away.
Thanks very much. Can you hear me okay?
Yes, sir.
Excellent. Well, thanks for that introduction. As noted, we're going to talk today about PFAS. We're going to talk a little bit about what it is and why we care about it. And then I'll talk a little bit about the federal rules that have been developing and also some Midwestern state rule development. Other states like New Hampshire, Massachusetts, other states out east have additional information, but that's not the focus of today's presentation. All right, ready? Let's go. What is PFAS? PFAS refers to a family of compounds, per and polyfluorinated alkyl substances. So alkyl, this is organic chemistry. Alkyl substances are straight carbon hydrogen chains. And these are the two PFAS compounds that folks most often think about. These are 8 chains, meaning they've got 8 carbons. Here's my cursor. 1, 2, 3, 4, 5, 6, 7, 8. And then they've got a functional group on the end. So these are synthesized chemicals. They are not found in nature. And the naming convention that we've got as shown on the left for these two 8-chain compounds refers to the P, which is poly or per. So per means fully substituted. These fluorines have taken the place of what was a hydrogen. And if all of those potential hydrogen sites are replaced, then it's perfluorinated. If some of them are replaced, it's polyfluorinated. The F refers to the fluorine. The carbon-fluorine bond is one of the strongest in nature, so it makes it very difficult to break down. We'll talk about that a little bit later. And then the O in these names refer to the octa, which is the length of the carbon chain. So here it's 8. Other compounds have different lengths of chain. 6 would be hecta, hexa, etc. And then the A or the S is referring to either the sulfonate or the acid functional group. Much of the attention that's been paid by EPA and states have focused on these two compounds, the PFOS and PFOA. And they were generally phased out of production in the US based on some concerns about toxicity and exposures. But you will hear about replacement chemicals such as Gen X or 6-chains or 4-chain PFAS compounds. These are emerging contaminants within the PFAS family, getting attention from EPA and other states. Compounds you might hear about names such as PFHXS is a hexasulfonate. You may hear about that in talking about firefighting foam. PFSHXA is a degradation product of the sulfonate. So I refer to these families, and what I'm talking about is, so if any of these individual compound substitutions, these sites with fluorines that may have other substitutions or may not be fully fluorinated, can create a slightly different chemical signature and possibly potentially different toxicity as well. So this variability leads to a large family of PFAS compounds. Currently, they're projecting around 5,000 or so different chemical formulations. So there's a lot of different compounds within this family. I've been around long enough to remember the dioxins and furans and how that sort of boiled down to a single number of TCDD equivalents and recalling the carcinogenic pHs that, expanded their list of compounds that would be additive, and you ended up with a benzoylpyrene equivalence. We don't have a PFAS equivalence yet, and we're probably a ways away from having it. So that's what PFAS is from an organic chemistry standpoint. Let's talk a little bit about what the properties are, which gets into why we care about it. So these are compounds that have been used because they've got useful properties. They're heat, oil, stain, and water resistant. Stain resistant, water resistant, grease resistant. That's great stuff. I love my raincoat shell being water resistant. I like being able to have stuff spill on my shirt and not have it stain. Making food is easier with nonstick coatings. You get it. They're useful. They're in a lot of products. The food industry in particular, the food packaging industry, has a lot of PFAS historically because of the grease resistant things. You can think about going through a fast food restaurant and the wrappers that are used to cover up that greasy burger, usually have some sort of coating on them to make it so that that grease doesn't leak through that and onto the bag and onto your clothing or your car seats. So this is one of the main properties that makes PFAS so useful and why they're so prevalent. They've been used in a lot of consumer goods. Another property that makes them pretty useful is their high durability in heat and its ability to form foams. So this film forming capacity makes it really useful for things like firefighting. And the reason that it forms films is back to the organic chemistry. We have a long chain, which is essentially a non-polar chain. I'm going to go back up just for a minute to the chemical structure. So here we have the non-polar part of the compound, and here we have the polar part. And again, I'm getting into a little bit of organic chemistry, so I apologize, but what you need to know about this is this part of the chemical of the molecule acts differently than this part. And so these parts tend to want to stick together and these parts want to stick together, which means that if you put a bunch of them together, they'll sort of form a film over the surface of your liquid that you've got them in. So they're really useful in firefighting. Class B foams, what we're talking about here. So what else is interesting about PFAS? They're resistant to biodegradation. So those consumer products that we saw earlier can end up in a landfill. More broadly, though, they're semi-volatile, so they can volatilize a little bit, but not readily. They also have some affinity for organic carbon. It's useful in water treatment applications, that particular characteristic, but it has limitations as well because PFAS is not the only thing with affinity for organic carbon. So I've got a picture here of landfills, but that's clearly not the only place we find PFAS, or we wouldn't have much to talk about today. Let's look at a hypothetical area and how PFAS might be present in that. All right, so this is one of my favorite slides. I'm going to stay on this slide for a minute or two to talk about how PFAS moves around in the environment. We'll talk about the regulations that are affecting each of these as this talk goes on, but just as by way of introduction, we've got generic sources over here on the left that may have stack emissions. So these stack emissions may release PFAS compounds into the air. We know from other site locations that those PFAS compounds can be transported miles, dozens of miles, and that PFAS falling either through precipitation or just aerial deposition can have effects on water quality, surface soil, surface water. There are things like background rainfall studies that are currently being conducted. Just to highlight this point, it was over a decade ago that they identified polar bear blood as having PFAS in it, which really just speaks to the widespread distribution of PFAS in the environment. So these sources, generally speaking, so we've got, industry here and more of a commercial, industrial, but residential stuff as well. Commercial and residential areas can be sources as well because PFAS find their way into a lot of consumer products. We find that septic systems are often a source of PFAS as well. Smaller scale, of course, but also can be significant loading to localized sources. So this figure depicts some aerial sources from other industries. it represents deposition and migration through the unsaturated zone. So there's your leach field, if you will, allowing the PFAS to travel down into groundwater. You can have the landfills that we talked about earlier. Those can be sources of PFAS, can be receptors of PFAS. Landfills don't generate PFAS, but they receive it from everybody else. And that's a lot like the water treatment plants. They don't generate PFAS, but they handle it, they receive it, and then they're sort of stuck with dealing with it. I noted here the groundwater can be a receptor for PFAS, and that's significant because a lot of folks get their drinking water from groundwater. I saw last night that 74% of private wells, 52% of cities in South Dakota use groundwater as a drinking water source. So, I mean, that's over half the population use drinking water as a water supply source. So really anything that goes into the air can be deposited somewhere, it can infiltrate into the ground surface, can get into the groundwater, and then subsequently be transported to groundwater extraction locations like a water supply well for a private person or for municipal entities as well. I want to talk a little bit about the other things in the figure. This water supply, well, biosolids, leachate, wastewater treatment plant. Wastewater treatment plants generate biosolids. So as part of the wastewater treatment, you get a organic rich material, very high in water content, and that's a waste product. It has traditionally gone to landfills or has been land spread as a fertilizer because of the high organic carbon content. Very few wastewater treatment plants are set up to treat PFAS right now. And so there's PFAS mass that leaves with the water discharge in the effluent. And there's also PFAS mass that ends up in the biosolids. So the biosolids themselves are an interesting story. They've been spread on fields as well as been placed in landfills. But there are some concerns about uptake from the soils to plants, and then from plants to grazing animals, and perhaps from those animals to humans. We're not showing any cows or pigs or chickens here because I'm not going after any particular specific industry. Just wanted to note that that is a potential exposure pathway that regulators are looking at. There's a site in Michigan that recently had a beef advisory put out because they had PFAS impacted biosolids spread on their fields. The cattle were grazing exclusively in that area, or largely in that area, and the state put an advisory out on the level of PFAS in the tissue in those cattle. So I mention this because PFAS has been widely used. It still is. And really the purpose of this figure is just to show that it's really everywhere. Once it gets into the environment, it doesn't break down very easily, and it can travel from one media to another, from soil to groundwater, from groundwater to surface water, or the other way around, depending on what your pumping systems are here. It's widely used. It's a large family of compounds. But why is that important? Why should we care? Well, for those of you who've been following the developments of PFAS regulations, you're probably aware that the science around the health effects of PFAS is evolving. In November 2021, EPA issued new scientific data addressing drinking water risks for PFOA and PFAS. The new reference doses, so I'm not a toxicologist, but there's reference doses which talk about how much of a particular compound gets plugged into the equation, causing an effect. And they're about 4 orders of magnitude lower than the reference doses previously used in 2016. Now, that's not necessarily a linear relationship, so we wouldn't necessarily say 70 parts per trillion is going to go down 4 orders of magnitude. But I offer that just as a point of reference that these agencies have been continuing to conduct additional research and have been reducing the concentrations that are used for advisory levels as time goes on. EPA, as part of their strategic roadmap, which I'll go into more detail later on, continues to develop a proposed PFAS primary drinking water regulation for publication. And so that's going to be some additional information for folks to keep an eye on for the drinking water world. And I believe Mark Mayer talked about that a little bit yesterday in his presentation. So here's a graph. What I really want you to see here is this is a log scale of concentrations. So this is criteria or advisory levels. On the x-axis is time. So what's the point here? The trend is downward over time, 2000, 2004 to 2020, 2022. We see states reducing concentrations of their recommended limits or advisory levels. And we see that those health-based values, the regulatory standards, are dropping over time. And again, this is a log scale. This is not an exhaustive list of PFAS drinking water values. There are states that have MCLs more than just the health advisory limits. Massachusetts, Michigan, New Hampshire, New Jersey, New York, Vermont. A lot of those are out east, but Michigan is a little more Midwestern. So the point is the toxicity is evolving. The standards are, generally speaking, going down. Okay, so we've learned a little bit about what PFAS is, why we should care about it. It's everywhere. There's some concerns about its toxicity. What is the federal government doing about this currently? So they've released a PFAS strategic roadmap, and this is sort of an add-on to the EPA's PFAS action plan, but it goes quite a bit further than the one that was developed under the Trump administration. So this is the Biden administration edition. Key points here. Sources are the focus. So while EPA's PFAS roadmap outlines multiple priorities, the agency's intended focus is on sources. So really they want to look at PFAS prevention, take a look at lifecycle considerations, release accountability, and historic and ongoing release tracking. They propose to build out within existing regulatory frameworks. So the roadmap focuses on regulatory mechanisms and environmental authorities that are already in existence to address PFAS contamination, includes RCRA, CERCLA, TSCA, NPDES permitting. The formal regulations development is ongoing, but the roadmap shows EPA's intention to increase reporting and compliance through regulatory requirements. There's a multimedia focus. The previous slide a couple back showed that PFAS can be in lots of different media. Groundwater and surface water have been the primary media focus for PFAS research, but soil and air are going to be getting additional consideration moving forward as well. Sorry about that. Life cycle analysis, they want to make sure they understand where it goes from cradle to grave, and disadvantaged community protection. There's also a component of the roadmap that incorporates broader environmental justice implications for potential and contributing PFAS sources. As more entities evaluate their environmental justice impacts and environmental, social, and governance ESG policies have PFAS implications, business decisions are going to, it's just my opinion, but I think they're going to transcend beyond just the regulatory framework. It's going to go beyond compliance based on some of these additional consideration. Now, this is a roadmap, right? It's not an immediate set of actions. Addressing PFAS is likely going to take decades, but the EPA roadmap outlines current and future actions and priorities. Within this timeline, it's, I think, intended that the states would be able to move forward and develop their own strategies where they're able to. So high-level overview, what's going to be coming down the pipe? Effluent PFAS limits, Clean Water Act, NPDES, effluent limit guidelines, air emissions like TRIs under the Clean Air Act, drinking water under the Safe Drinking Water Act. And then there's a regulatory authority expansion under CERCLA. That's going to include giving regulatory agencies the ability to compel investigation and remediation. It's going to increase liability for folks who receive, handle, manufacture, possibly even transport PFAS-related materials. And again, the the goal here is source reductions. They're trying to take PFAS out of the environment. So I'm going to go through these just a little bit more detail, just to give you a little bit more information. PFAS water regulatory developments. So they're looking to establish a maximum contaminant level. An MCL, right now they've just got a HAL, health advisory level. Expanded list of PFAS compounds, 29 compounds instead of just the 2 that we were talking about earlier. They talk about restricting the PFAS discharges using effluent limitation guidelines. And they want to put forward, there's a place where the preliminary plan 15, I'm going to get a little technical, was announced in September 2021. And that's where EPA evaluates the effluent guidelines every 2 years. And they're revising the limitations for a couple industries, the organic chemicals industry, plastics and synthetic fibers, and metal finishing industries. So they're calling out specific industries. And so that sort of adds a layer of complication to how you would track your PFAS regulatory requirements. So I offer this as a bit of additional information so that folks can understand what might be coming their way in terms of the water and drinking water. Safe Drinking Water Act, it's the first step in the safe drinking water regulatory process. Public comments are closed, and so this is sort of an in-process activity. Again, I think Mark talked about this a little bit yesterday. They're looking to make final determinations to regulate PFOS and PFOA in drinking water. That rule is expected to become final in fall of this year. I'm sorry, the proposed rule is expected in the fall of this year, and the final rule is expected in 2023. And then I think you can look for additional compounds to be added to that list as time goes on, as the science develops. UCMR 5 is sort of that next step. We talk a little bit in the industry about what analytical methods can be used to understand this. So as the science develops, we find that the concentrations that are being asked to be met at a point of discharge continue to go down because of toxicity information that folks get. And that's really pushing the laboratories, the commercial laboratories, to better analyze these compounds. Now in water, it's pretty well established. Wastewater is a little bit trickier because of that media. EPA is putting out some guidance on additional analytical methodologies for other media, soil, and other high water content things like biosolids. So there's a variety of analytical methodologies that are moving forward as well. So we talk here a little bit more about the PFAS discharge limitations. We'll talk about this a little bit more in the states because some states have been moving forward on this already. Numerous states have implemented their own criteria or put out draft criteria for folks to observe. Monitoring the NPDES permits is something that is likely to come forward. You can expect those requirements at facilities where PFAS are present or expected. Other conditions of the permits might be product elimination or maybe some BMPs for facilities that hold or have to hold AFFF, the aqueous film forming foam. And there's multi-lab, this reference to the method validation as an analytical method. It's a multi-lab verification that's going on currently to validate that method. They've had single lab validation already, but additional steps are being done to try to make that a more permanent method. So infrastructure and job acts, there's quite a bit of funding coming our way. I see I'm getting a little bit behind in my time, so I'm going to move a little bit more quickly. TRI reporting. So this is your out of the stack. This is a transition to air. Additional PFAS compounds were added to the toxic release inventory reporting, and they removed the de minimis eligibility from supplier notifications. So it sort of increased the level of scrutiny on whether or not the products that you're bringing into your facility contain PFAS or not, whether intentionally or as a byproduct. That categorizes PFAS as a special area of concern, chemical of special concern, which again sort of increases the scrutiny. And then the proposal to designate PFAS as a hazardous substance has some pretty far-reaching implications. I show the image of money here because it's sort of a liability issue. The draft before the OMB is expected in the advanced notice of proposed rulemaking is expected in June of 2022. The final rule is expected in 2023. But what this would do as a listing of PFAS and PFOA as hazardous substances, it requires reporting. It allows other agencies to require investigation, potentially cleanup. It makes it part of a standard phase 1, phase 2. So even things like property transactions are going to have PFAS show its face in the consideration of what sort of environmental liability might be present on a property. Environmental justice. This is the first sort of big foray into environmental justice, and really what it's looking at is looking at disproportionate effects, negative effects on communities that have been disadvantaged. So there's some ongoing activities here. Some of the social trends associated with environmental justice have caused additional media scrutiny and public scrutiny. This graph just shows states that have either fish or wildlife advisories in place currently. So there's Great Lakes advisories for a couple different kinds of fish. Minnesota has fish advisories, Wisconsin, Michigan. There's a big push for subpopulation consideration. So folks in certain cultures who eat a lot of fish, for example, they're taking a look at what that subpopulation's rate of consumption is and creating guidance based on that. We're going to hit the Midwestern states briefly. Michigan has been leading the way in a lot of ways. This map shows PFAS sites exceeding their Part 201 criteria. So you can see there's quite a few of them. MPART is their Michigan PFAS response action team. And that has been a forward-looking group, let's say. They've been pretty aggressive about creating new regulations and implementing those. They've been looking for source areas as well. Their playbook a little bit is, let's take a look at water treatment facilities. Let's see who's got PFAS, and then let's start looking upstream to figure out where those sources of PFAS that are coming to the wastewater treatment plants are coming from, and then work with those facilities to figure out, is that an effluent issue? Is that a sourcing of materials issue? Do they need to have treatment? Can they reduce their sources so that they have fewer PFAS discharges going to the water treatment plant? Wisconsin, similar map here. You can see where PFAS has been identified across the state. Wisconsin is one of the states that's doing that ambient rainwater research that I was talking about. I've been tracking Wisconsin pretty closely. It's been kind of interesting to see them develop their surface water, groundwater, and drinking water criteria all in parallel. And it went to the Natural Resources Board for recommendation to move forward. And the Natural Resources Board took off the groundwater rule, modified the drinking water rule from 20 parts per trillion that the DNR had recommended, that the Department of Health in Wisconsin had recommended, and they increased it to 70 to match the federal health advisory level. And they left the surface water essentially alone, but they give it a long time for implementation, so that I think it's a 2-year monitoring period and a 5-year reduction period. The state got sued because they collected some water effluent samples from facilities that had permits. Those permits didn't include PFAS, but the state came and sampled them and analyzed them for PFAS. They got sued by a trade group. a judge ruled on it and said, well, you have the ability to sample and analyze and make those results public, but you do not have the ability until promulgated, until actually force those facilities to do anything about them. So it's been an interesting time in Wisconsin. Colorado is moving forward with some activities. A lot of it is focused on AFFF, but you can see here that there are drinking water concerns all across Colorado as well. And then finally, I'll talk about Minnesota briefly before closing here. The MPCA just released their final PFAS monitoring plan this week, and it is a multimedia extravaganza of sampling. They would like to take a look at your effluent, your air discharges. It's really broad and inclusive. The draft plan came out in November and the final plan came out this week. We're in the process of talking to clients about facility lists that are included in that plan. Originally, the MPCA said they were going to look at basically industry codes, NCAT, NCAIS codes. But in the end, they decided to just list facilities that they were going to be approaching and asking for sampling. There's additional bills that are coming forward for food packaging, drinking water, and AFFF as well. So I ran through a lot of information here. Parting thoughts. PFAS is in a lot of places. The science is still being developed, from how it travels and transforms in the environment to what degree and the different types of PFAS may be negative affecting health, to how they're analyzed. It's all evolving. Concurrently, and as a result, it's an active regulatory climate. It's going to continue to be. I would encourage folks to track their regulatory requirements by location, so both federally and state, or even locally if you've got some strong local authorities. Look at what industries are being focused on by those regulatory agencies, and if your industry is one of those, you may want to look a little bit more closely at what might be coming your way. And then by what discharge media? Are we talking about air or soil or groundwater, surface water? What's your discharge media? The last parting thought, really plan ahead. My advice is for industry groups to, it's important to understand the risk profile and develop a plan now. Because of the complexities of PFAS compounds and the regulatory climate, we recommend working with somebody who's got some experience with PFAS so that you're not really caught flat-footed in a rapidly evolving regulatory environment. I appreciate your time today. Got a little bit of time for questions if anybody has any. Thank you.
Yes, Kevin, thank you very much. We did just have a question pop up here. Are there laboratory analysis tools that can be used to infer source tracking information for PFAS? In other words, are certain individual compounds associated with firefighting foam or domestic sources that would be found in essentially all wastewater streams?
So the first part of that question is, can the laboratory help you figure out what your source is? The laboratory can tell you what your distribution of compounds are, and seasoned folks who've looked at a lot of PFAS data can tell you that your AFFF, for example, is going to have a very strong hexa signature. And so the term fingerprinting comes into play once in a while. I think fingerprinting is a bit of an overstatement, but you can get some information about what your potential sources might be based on what that chemical distribution of the different PFAS compounds are. I think that, in other words, are PFAS. So yeah, the short answer is yes, you can get some limited information about what the distribution is and make some inferences about what the sources of that PFAS, what might have been.
Great, thank you. Quick question for me. You talked about EPA's roadmap, and is there, and I apologize if I missed it, is there a timeline in there that they think they're going to meet some milestones moving forward?
Yep. Just going to go back to my notes there. I want to say late 2023 is when most of those individual efforts are going to be finalized. But it's pretty rapidly evolving. Some of the preliminary actions are moving more quickly than that.
Great, thank you. All right, I don't see any other questions. Kevin, thank you so much for your time and for your knowledge, and I look forward to seeing how this information connects to our next talk. So appreciate it very much.
Thanks, everybody.
So next on our agenda is David Waterman. David has been an assistant professor in the Civil and Environmental Engineering Department at the South Dakota School of Mines and Technology since 2017. His expertise is in river mechanics, sediment transport, and environmental hydrodynamics. He will be discussing the results of a preliminary sample effort undertaken in 2021 to quantify PFAS concentrations in South Dakota streams. Welcome, David. Take it away.
All right, thank you. Can you hear me all right?
Yes, sir.
All right. So I'm going to preface my talk by saying that I am not an environmental engineer. I'm a hydraulic engineer. I'm certainly not our local expert in PFAS here at South Dakota School of Mines. But we do have a good team of people working on it, several of which are my collaborators here, Brett Lingwall and Lisa Kunze. I'm certainly glad that Kevin's talk went before mine because he's certainly able to explain a lot of the chemistry and regulatory aspects of it that way better than what I could ever do. So with that being said, my presentation has 4 components. I'll give you a little bit of background information, talk about our sampling and analysis methods. The biggest part of the talk will be in the results, and then finally some conclusions. So the first outline item, which is the background information, most of this stuff Kevin covered, like I said, in greater detail than what I ever could have. Like Kevin, I refer to PFAS as the group, so it's kind of a generic term. If I'm talking about an individual compound, I'll refer to it by its letters like PFOA, PFOS. So I've got listed here 2,000 plus compounds are known. Kevin's talk had 4,000 to 6,000, so we know that there's a lot, and we don't even know all of them. We can, in the lab, only analyze for a few hundred of them. These are some of the main source areas or source products that generate PFAS. One of the things that he didn't go into as much detail in is the toxicity. One of the reasons why the PFAS has caused such public concern is this idea of it being persistent, bioaccumulative, and toxic. The half-life of these chains are, in years in the body. Almost everybody has PFAS compounds in their bloodstream. It stays in there for years. It circulates through the system. It gets excreted through the urine, winds up in sanitary sewage. It's also bioaccumulative and toxic at very low concentrations. So we're going to be talking about concentrations that are in the parts per trillion, which is very, very low. And then this is the structure, the hydrophobic tail, the functional group head, which gives it its surfactant qualities. Just as a frame of reference, this is a site in the Great Lakes. Again, you can see that these are samples that were taken in surface waters, just as a frame of reference to compare with what I'm going to be showing you, which is going to be pretty small concentrations of PFAS in the surface waters of South Dakota. We're, for the most part, sub 10. But just as a frame of reference, this is in the Great Lakes region, more specifically Green Bay. You can sort of see the distribution of their compounds. When they did their analysis, they analyzed for 11 different compounds. In our analysis, we analyzed for 43, but we only hit on 5 of the compounds, which happened to be sort of in this main group that they were also finding. The 5 that we hit on were PFBA, so that's a 4-chain, B being a butane base. Again, PFBS, that's butane base, HXS, that's a 6-chain or 6-carbon chain, and then O, that's octane. This particular data comes from Green Bay. It's an area that's currently involved in litigation. There's a Tyco plant that makes the AFFF, subsidiary of Johnson Controls, and they've got known offsite releases. But you can see that their typical values, most of their surface water values are falling somewhere between 15 and maybe 30, 35 parts per trillion. And then looking at the same region, the Great Lakes, in terms of the lake itself, this is from 4 of the lakes with a whole bunch of samples. You can see that the Great Lakes, these samples were taken in the upper 10 meters from this study back in 2019. Their typical concentrations are sum out to about 5 parts per trillion nanograms per liter, with Lake Ontario having the highest, 13.3. What's kind of scary, and Kevin hit on this, is the issue of the precipitation. That you can see that all these compounds are found in precipitation at a level of about 3 parts per trillion. So if you're if you're tasked with trying to get rid of this stuff and it's falling in the precipitation at a level that approaches the regulatory levels, then it's really a tall task and a daunting task. So moving on to part 2 of the talk, I'm going to be just very briefly talking about our sampling methods and the laboratory analysis. So the title of my talk was a reconnaissance level analysis, and that's all it was. It wasn't a systematic study. What we were up to is we were just trying to identify sort of baseline concentrations. Most of our samples were co-located upstream and downstream of wastewater treatment facilities and populated areas, with the goal being to just try to find, are there areas in our streams that are of concern and maybe warrant some more investigation. Again, these are discrete time, single time point samples, near surface grab samples. These samples are collected in special plastic containers that we got from Battelle. 250 milliliter samples, they get put on ice and then shipped back to Battelle. The laboratory analysis that we ran, or we had them run, was this top assay. The top assay is ran in 2 batches. The first batch, they run it through LC-MS, MS, just comparing against standards, various compounds that they have laboratory standards that they can compare against. And then the second batch, what they do is they oxidize the sample at high pressure and high temperature, which causes some of the precursor compounds then to turn into compounds that they can actually analyze with the LC-MS. So I think in Kevin's talk, he showed one of the 6,2 fluorotelomers. That's one of the precursor compounds that this laboratory analysis can identify. This TOP, top assay, it doesn't have an EPA number like the EPA 1633, but it does quantify 43 of our PFAS compounds. The detection limits range from 0.115 nanograms per liter. This would be one of the 6-chain PFAS, all the way up to 1.64 nanograms per liter. And the typical values are around 0.5 nanograms per liter, the detection limits that we're looking at. So that's kind of a sort of something to keep in mind when you're looking at some of the non-detects, is that's the lower limit there. So moving on to the results, we had 6 different sampling stations. All of these were centered around population areas, with the exception of the Cheyenne River stations. So the first set of results I'll show you is from Rapid Creek, the second from Cheyenne. The third set is from bounding the Pier area. The fourth area is bounding Mitchell. The fifth area is bounding Sioux Falls, and then the sixth area is bounding Yankton. So this is our Rapid Creek sampling stations. The triangles on here represent the samples. The flow of Rapid Creek through Rapid City is from left to right. The biggest part of the Rapid City area is serviced by sanitary sewerage, which then goes down to our water reclamation facility down east of town by the airport. So our most downstream sample was down below the wastewater treatment plant. Sample 2 is kind of in the middle of town. Sample 1 is basically at the upstream end of town. There's really, we took the sample thinking that it was going to be sort of our reference. We weren't really expecting to find anything because there's really nothing upstream of there. There's a few very small communities. There's Silver City, Hysiga, but there's very little population up there. But nevertheless, as you'll see, we did hit some compound. The way that these results are going to be presented, well, typically I'll have my concentration plots stacked up similar to those previous studies that I showed. And then down below, I've got some discharge information just so you can see what sort of flow rates that we had during our sampling event, and how that relates to, say, a base flow condition or just an average flow condition for that time of the year. So at Rapid Creek, you can see at our upstream sample station, we hit PFBA at about 4.2 nanograms per liter. That was the only sample that we hit PFBA. I'm not sure why we were finding PFBA up at that site. Moving downstream, you get a profile that's more similar to what you expect. The sum of all the compounds, about 4.5 nanograms per liter. We hit PFOS, PFHXS, PFBS. And then going downstream to the down below the wastewater plant, then we get up to about 10.5 nanograms per liter, where we've got the same 3 compounds as over here, but we also have this PFHXA. And again, these six chain PFAS compounds tend to be more closely associated with the firefighting foam. In terms of the flow, if you think about this in terms of loading, the conversion factor, if you have 1 nanogram per liter times 1 CFS, that's going to equate to about 2.5 milligrams per day. So for instance, if we've got 10 nanograms per liter and 100 CFS, then you would multiply this value by 1,000 to get the loading. Also, it's just important to know where are you at relative to the base flow, so you can make some sense of those concentrations. You can see here when we sampled in May of 21, we were way below average for these 2 gauges. But it was considerably higher than what would be considered like a wintertime base flow, which would be closer to 20. So those are just a context in terms of the flow by which to think about these concentrations. Moving on to our second sample site, Cheyenne River. Just for context, the Cheyenne is going to be draining the biggest part of western South Dakota. This is the main stem Cheyenne. This is Rapid Creek, where we just were. The lower limb of Cheyenne River is going to be draining all the communities in the South Hills. This is the Belle Fourche up here. It's going to be draining all the communities from North Hills and Belle Fourche, Sturgis, Spearfish, etc. Of particular concern is this feature here. This is Box Elder Creek. We know that it's problematic because the Ellsworth Air Force Base is located in the Box Elder Creek Basin. They know that they have contamination that's extending off-site. So that's obviously going to be a trouble area. So we're down way at the downstream end, just trying to get kind of a big basin view. And then we also caught one at the upper end of Lake Oahe. The samples there, as you can see for Cheyenne River, hit basically the same ones that were in Rapid Creek, a little bit higher concentration, 10.78 nanograms per liter. So Rapid Creek was running 70, 90 CFS. Cheyenne River at the time was running very, very low. So anybody that got to drive or experience the Cheyenne River last year saw it very, very low throughout the spring and summer. So I think it was running roughly 330 CFS when we were out there, probably lower than you know, what you would typically expect it, which might suggest that this concentration might be a little bit high if there was more flow coming in, but the verdict is out on that. Whether those concentrations stay relatively constant with flow, or if they are strongly dependent on the flow. Moving into the lake, the only compound that we hit is the PFHXS. Again, that this partly would be explained by the lower detect limits that the PFHX compounds had, but naturally, you know, the biggest part of the volume of Lake Oahe is from Missouri River water. Presumably that water is going to be coming in cleaner in terms of concentration than the Cheyenne River. So that's partly explaining that lower concentration level, and definitely lower than what you saw in the Great Lakes. Moving on downstream, this still is Lake Oahe, and our sample station 3 was bounding Pierre. Sample station 1 was upstream of the town of Pierre and Fort Pierre. So sample 2 was downstream of the wastewater inputs. So this is the wastewater treatment plant of the town of Pierre. Fort Pierre, they have wastewater treatment lagoons over off of the Bad River. So their wastewater ultimately winds up draining through the Bad River into Missouri. And then our sample station was then downstream of that, down by Farm Island rec area. And those samples, as you can see, are pretty clean. PFHXS was the only one that hit at the upstream station at about 0.2 nanograms per liter. Sample station 2 didn't hit on any of the compounds, and obviously you've got you know, a strong dilution effect. Fairly high flows. We were running somewhere in excess of 25,000 CFS when we did this sampling. The mean daily mean values or monthly mean values are what's shown here. That are obviously on the Missouri River are going to be pretty high. Moving on to the fourth site, James River. So there's this is the town of Mitchell. This is the James that flows down in this direction. There's another drainage way of concern in Mitchell. This is Fire Steel Creek that runs down through here. Mitchell is served by sanitary sewerage, and their wastewater treatment plant is down in this area. So the next slide I've got zooms into there so you can see what's going on with respect to the water treatment plant and our sample sites. So again, this is Fire Steel Creek. The wastewater treatment plant drains into a little drainage way that goes into Fire Steel Creek, and then Fire Steel Creek goes into the James. This is the freeway, I-90. This is Highway 38, and our sample 1 was taken upstream of Fire Steel Creek. Sample 2 was downstream of Fire Steel Creek. In those 2 samples, the results of that you can see at the upstream station. It was a fully non-detect. The downstream station down below Fire Steel Creek, it hit PFOS and PFBS with a sum of about 3.5 nanograms per liter. The James River at the time of our sampling was running exceedingly low for the time of year that we sampled. Somewhere between 300 and 400 CFS. which is approaching a base flow level and way below the mean daily discharge for this time of the year. So again, thinking of these concentrations, you know, if whether that would potentially change if the upper James was generating a lot more water relative to Firesteel Creek, then these values could certainly change. Moving downstream or to east in the state to the Big Sioux. This is the Big Sioux River that runs around town. Our upstream station was upstream of the diversion, upstream of the airport, which would potentially be a source of firefighting foam contamination. This is the wastewater treatment plant. This is the town of Brandon. Brandon, if I understand correctly, is currently pumping their sewage over to Sioux Falls Water Treatment Plant. And there's a drainage way that comes, that emerges out of Brandon, and we wanted to get down below that for our sample station too. The results here at the upstream station, again, it's up above the diversion. The only sample or the only compound that we hit was PFHXS at about 0.8 nanograms per liter. And then we get down below the wastewater treatment plant in Brandon, and we hit these three that are the most common compounds that we hit in the various sites: PFBS, PFHXS, PFOS at a sum of about 4.3 nanograms per liter. The flow in Big Sioux at that time was somewhere in the neighborhood of 400 CFS, so more closer to a normal flow level at that time of year, but still low. And then finally, the last sample station was here, Missouri River at Yankton. This is Gavin's Point Dam. Our sample one was just downstream of the outlet works. The town of Yankton sits here. The James River comes in here, and then we were way down here, probably not too far from the Wellfield down by Vermilion that the first speaker talked about today. So this was our sample station too. And what we found here, again, very similar to by Pier, was very low concentrations. The only thing that hit was this PFHX compound, which again had one of the lower detect limits, about 0.2 nanograms per liter. Again, the Missouri River down here was approaching 30,000 CFS when we sampled. So there's obviously a lot of dilution effect, and certainly has a big bearing on these very low concentrations. So to wrap things up, the final outline point is the conclusions. 6 of them here. What we found was detectable but low levels of PFAS present in the large South Dakota waterways. Levels considerably lower than the current EPA advisory levels. However, as Kevin pointed out in the previous talk, that the regulatory climate is very fluid. So although 70 PPT might be what people are shooting for now, you saw values in Michigan that were down closer to 10 nanograms per liter, and we're seeing those types of concentrations in Cheyenne River, Rapid Creek. So probably the most significant of these is point number 3. Population centers are associated with discernible but modest increases in PFAS concentrations in the receiving waters. We saw that at Rapid City, we saw it at Mitchell, we saw it at Sioux Falls, that up and downstream of town, that the concentrations increased. The PFAS concentrations that we found were not big. There wasn't anything that was terribly alarming to us from evaluating those concentrations. But although those concentrations are small, we need to be concerned or aware that it may be a concern of this idea of bioaccumulation in aquatic organisms. As we expected, substantial dilution effect associated with Missouri River, the high flows. And finally, in terms of the sources, where this stuff is coming from, between point source and point source contamination, that is unknown. If we're going to look further, certainly the effluent from the wastewater treatment plants is something that probably would warrant some additional investigation. But that's what we found, and with that, I'm glad to take any questions that you might have.
Sure, David. Here's one that just popped into the chat.
Okay.
Is PFBA currently a constituent of forest fire fighting foam? Just looking at the small concentrations found in Upper Rapid Creek during the study and thinking of possible connection to the Schroeder fire, which took place directly upgradient of that area in March 2021.
Yeah, I'm not sure if PFBA is one of the compounds that are found in the foam. I mean, that's a great correlation or observation that may have been the source. I looked around. I'm not a PFAS expert. What I found for the various compounds, this was from a site called the Environmental Working Group, that for the PFBA, they indicate that it's a breakdown product of stain and grease-proof coatings on food packaging, couches, and carpets. Now, that's not to say that it's not in the firefighting foams. I wouldn't want to say definitively one way or the other, but I think it's probably a very good hypothesis.
Okay, what is the cost per sample for the analytes you were looking for?
If I remember correctly, they were to run that top assay on single samples was between $200 and $300 per sample.
Okay, could you explain what bioaccumulation is?
So bioaccumulation, if you think of, for instance, in Lake Oahe, we saw concentrations near the outlet of Cheyenne River at about 1 nanogram per liter. So if you've got various plankton, microinvertebrates that eat the plankton, maybe the plankton is going to, in their cellular structure, is going to have similar concentrations as the water. So it might be at 1 nanograms per liter, and then the microinvertebrates eat up all the plankton, and then they start to accumulate that. What they excrete out of their body in terms of PFAS is less than what comes in, and then maybe the invertebrates get eaten by little fish. Again, it accumulates more. They take in more PFAS than they excrete, and so just because the water is at 1 nanograms per liter doesn't mean that the fish tissue is going to be at 1 nanogram per kilogram. It may be considerably higher. And in humans, the longer chain compounds tend to accumulate more. The shorter chains, like the PFBA, the 4 carbon chains tend to pass through. The data that I've seen is that the smaller chains tend to accumulate more in fish. There's in terms of the bioaccumulation and toxicity, there is a lot of uncertainty. There's a lot of study that needs to be done.
Okay, and then we just had one comment here pop up from Sean, who's a firefighter on our staff, about wildfire foam not having the PFAS in it. So thank you for that, yeah. Sean. All right, David, thank you so much for that presentation. We appreciate it. Thanks for being with us today.
Yep, thank you.
Okay, moving forward, our next speaker this morning is Denise Cox. She will talk about sustainable development. Denise is the past president of the American Association of Petroleum Geologists and current distinguished lecturer on sustainability. She will share her observations on energy in transition, sustainable development, and the life cycle cost benefits of energy choices. Welcome, Denise. Are you perhaps on mute, Denise?
Good morning, and thank you for the invitation to speak. I've been very impressed with the speakers in the last 2 days and the attendance to this conference. I'd like to encourage you to be more involved with AAPG's Division of Environmental Geoscientists. You have a lot of very good information to share, and it needs to reach a broader audience. So today we're going to talk about energy in general, and I'm going to focus on South Dakota because we are a little bit time limited. So the talk will be broken in 3 parts, so you can take appropriate stretch breaks. I will talk about sustainable development and energy realities, take a lifestyle look at all energy, specifically focusing on South Dakota, and then talk briefly about energy and transition and uncertainties. And shown here on the right is my husband, Kurt Cox, and it's one of our storm energy sustainability projects. He has picked up in over 10 years, over 3 tons of plastic off northern Florida beaches. So what is sustainable development? It's defined as humanity has the ability to make development sustainable to ensure 2 things: that it meets the needs of the present without compromising the ability of future generations to meet their own needs. And if you take nothing else from my talk today, we're all needed. Geoscientists and engineers are essential to meet the sustainable energy needs of both the present and the future. For today's talk, we're going to focus on Sustainable Goal 7, affordable and clean energy. So how is that defined? It's a simple definition to ensure access to affordable, reliable, sustainable, and modern energy for all types of energy. But I'd update this now based on what we're seeing globally is secure energy for all. And there are a number of things that are happening on the geopolitical realm that we need to be aware of, and we'll touch on those briefly. So let's define all. So here's the world population from basically the beginning of time. And today we have about 7.9 billion people who need energy today. Put that in perspective. In 1804, there were 1 billion people on the planet. By 1970, that increased to 3.7 billion people. We're here, we are today, and we're projecting 10 billion people will need energy in 2057. So the population is growing and our need for energy is growing. And we can see that if we look at just the time slot between 1970 and 2019, where we had 3.7 billion people in 1970, that's, I think in terms of barrels of oil equivalent. So that's about 37, 38 billion barrels of oil equivalent, increasing over 62% to where we are today. Almost 100 billion barrels of oil equivalent energy is needed. And that makeup globally, not US, but globally, is over 81% fossil fuels. Smaller amounts, 17%, nuclear, hydro, biofuels, and waste. And a very small wedge and growing is solar and wind. That's the energy reality. But I want to look a little bit closer to how we're using it. The big uses are obviously industry, transportation, and residential. And when we talk transportation, that is really the main use of liquid hydrocarbons is in transportation. But what I'm going to focus on next is this wedge here shown in this teal color, and that is the electricity. We hear a lot about electricity and converting from fossil fuels to electricity, but there's another energy reality for us. The resources that are powering electricity are still predominantly fossil fuels, 63% coal, oil, natural gas. A growing wedge, importantly, nuclear, hydro, biofuels, and waste, and our smaller wedge, 8% from solar and wind. If you take the second thing we need to take is when we're talking about electricity, we're still talking about fossil fuels. So how can we do this better? How can we ensure access? So let's define that. So here's access to electricity globally. Over 13% of the world, predominantly in sub-Saharan Africa, does not have access to electricity. But more importantly, if we look at a graph of who does not have access to clean fuels for cooking and boiling water, and by that we mean good health, over 40% of the world, a very large segment of our planet, does not have access to clean fuels for cooking and water. So let's move on to the next concept, and that's affordable energy. And what I've plotted over here from our world and data is the levelized cost of energy. So that includes the plant construction, the fuels, the operating costs. It's a more holistic look at energy. And here's coal, kind of our baseline. The world ran on coal for a very long time and is responsible for our industrialization of our planet. So coal is steady, about $109 dollars per megawatt hour of energy created. But everything else is coming down. Our ability to generate power from gas generated at peak times, onshore wind. One of the major decreases in cost is our solar voltaic cost, decreasing over almost 90% decrease in cost. And larger solar thermal plants, not a major part of our energy market, but that's also decreasing. But a very good talk yesterday by Dr. Omie, I think that's how we say it. The cost for nuclear is increasing, and that does seem to be a US phenomenon, but it shouldn't be, because it is a very important source of clean energy. And I think we're going to see changes in that in the future. So reliable. One way to look at reliable is how it affects us as individuals. And that is, generating power for seasonal variations, double peaks in winter and single peaks during the heat of the day in the summer. But what it means to us in terms of energy is, how do we meet the base load? Nuclear, hydro, coal, and gas meeting the base load of our energy that we generate during the day, during our 24-hour cycles. But dispatchable generation is what many people don't understand. And that's electricity that can be transmitted on demand. And there are lead-in times for this. And we're looking at how we import power across state lines from different facilities, flexible hydro, something very important to South Dakota, and combined basically natural gas power plants that can be turned on quickly. But the big thing we're seeing now, especially with brownouts and blackouts, is peak matching. And that's efficiently using our hydro peaking generation and gas peaking. But when we talk about reliable, I think what most people think about is storage of these intermittent sources. And when we think about storage, we mainly focus on batteries. Some pumped hydro where we can store and increase the flows in hydro, but where we're heading, and not enough time to talk today about it, is long-term storage. And this is power to gas. And it really involves the hydrogen economy and what's to come. And maybe that's something we can talk about next year. But while I'm on storage, I'm going to pause here. And there's a lot of very good talks and a lot of attention being paid to this in the medium now, is what, as geoscientists, what do we as hydrologists need to know about what makes up batteries? So if we just look at cobalt right now, the cobalt resources on the left here is where we're developing our cobalt resources now, predominantly the Democratic Republic of the Congo. And where are the future resources? Again, the Democratic Republic of the Congo, Australia, and a mixture of other places. Where's our lithium? Currently, almost all of our lithium is coming from Australia, but the future development is going to be in South America, Chile, Argentina, and continuing with Australia. But the last one that we need to look at is components of storage and batteries, and a lot of our alternative energies really rely on some component of rare earth elements. And these are associated with development in the Asia Pacific areas. Again, currently in China, Australia, a little bit in the US, Vietnam, but where are they in the future? Again, China, Australia, and Vietnam. So our geopolitical relationships with energy are shifting from US-based, Middle East-based to more globally based, and we need to be aware of how these are affecting our development of resources. So in summary, resources are in transition. We're seeing a growth in demand for strategic resources. We're seeing a shift in geographic location. It's not just the environmental footprint and the social footprint of mining, but it's processing and transportation. We may be mining on one continent and shipping it, transporting it in another to be processed. And these are the hard facts. Lithium may be produced in the future in South America, but it may be processed partly in Chile or shipped and processed in China. Same thing for cobalt, nickel, a wider variety of places being processed. But we're watching all of these things. And I want to say this as environmentalists, and I am a legacy member of the Nature Conservancy, we need to be holding the line that we all are developing these all of these resources the best way we can. And with that, we need to be mindful of geopolitical power. That brings us to sustainable development. This is the third thing you should take away from this talk, is this is a framework. It is not saying that one type of energy is better than another. It's saying we need to look at how do we economically develop resources? What is the effect on social progress, social programs, and what is our environmental responsibility? That's what, to me, is our job as resource geoscientists and engineers. So for this talk, I've just broken it down to 3 things so we can kind of have a metric on how we're doing for sustainable development. This is one of my favorite slides because it talks about why have we developed the energy that we've developed so far. It's power density. Natural gas, nuclear, oil, coal have very high power densities. So a small volume of product gives you a large ability to do work. Where we're heading now is alternatives. So as we decrease their power density, we're increasing the amount of product it takes and the footprint of that, which brings us to the second thing. No surprise that the minimal surface infrastructure, most of these resources were underground. So we weren't seeing a lot of their physical presence. But as we continue to develop resources, we're beginning to hear more and more comments that we don't want these things developed in our neighborhoods, specifically solar, large footprint of petroleum shale gas, hydropower and its effect on our sources, and wind. And we'll touch on that a little bit later. But something you're probably much, much more familiar with in South Dakota than I am here in northern Florida, a little bit. We have a huge footprint on biomass and biofuels. So we're going to see an increasing social interaction of how we develop resources to meet the needs of the present without compromising the ability of future generation to meet their energy needs. And that's the last thing. We have a lot of focus right now that the environmental impact of energy is CO2. And yes, alternative energy has an order of magnitude lower CO2. These are grams of CO2 equivalent per kilowatt hour generated. But globally, we're at about 475 grams of CO2 equivalent per kilowatt hour. And this is for electricity generated. And that is really 2 things. It's natural gas taking over coal, but it's also the balance between biomass, co-firing, and regular biomass plants that are helping to levelize that. Where we're heading is focusing more on alternative energies, but we are not there yet. So when we talk about modern energy, we really need to talk about an energy mix. How do we use our existing energy better? How do we improve efficiency of the energy that we're developing? And how can we efficiently and strategically develop new infrastructure and facilities? Those are questions that I don't have the answers to, but they're questions that we as individuals need to be asking. We as scientists and engineers need to be helping. So I want to take a life cycle look at energy. So this is part 2. And this is my home from 2018 when a Category 5 hurricane hit Panama City, Florida. We had no power. So the realities of having no power and what that means to access to electricity, water, basic sanitation were brought home. It's a very difficult process. 3 years later, we're still rebuilding infrastructure to serve the city. So let's look at South Dakota. I don't have enough time to go into all of the things, but we're going to focus on what South Dakota does well, and that is hydro, wind, a little bit of coal just for perspective, and natural gas. This is what is generated in state. But it was interesting to me when I looked at what is being consumed in South Dakota. Again, we see the hydro, the wind, natural gas, but quite a bit of coal. And I suspect that's being imported over state lines in forms of electricity. And you have no nuclear plants in South Dakota, but you do import some energy that is based there. And purchased energy is a number of different things that feed into this mix. So let's start with coal. I always like to start here because it is what's gotten the most attention and what has changed the most in our recent history. So on the left of all these slides, we'll see the accessible, affordable, reliable, and due to time, I'm not going to go over these, but these slides will be available to everyone in the conference today. But I want to look at sustainable. Yes, why do we develop coal? It's economic, high power density, and the facilities have a long lifespan. It's been very difficult to get them to switch from coal to nat gas to alternatives because the plants are still viable. This picture here is from Poland. This is the #1 polluting power plant in the world. And for the life of me, I cannot understand why we have not been able to put some type of carbon capture project immediately on this one plant. If we can just do one thing, we can make a difference. So what is the environmental footprint? Obviously, the land use intensity in most part is low because the mines are subsurface. This one has a high lignite surface mining footprint. Emissions are extremely high, over 820, I want to say that's gigatons of CO2 equivalent per kilowatt hour. But more importantly, I used to work coal bed methane in both Wyoming and the UK, and the acid mine drainage and runoff is important, and the mercury and heavy metals associated with that are important. But what's the upside? And these are the social comments. Coal is what underlies the industrialization of the world. It got us to where we are today so we can make better decisions. We can actually develop resources better. And there's a strong history of mining cultures. My grandfather was a coal miner in upstate New York, southern central New York. And that tradition underlies a lot of the cultures all over the planet. I do encourage you to visit Poland. It's a fabulous mining museum there. So is it modern energy for all? There's resources and infrastructure. Existing power plants can be combined with carbon capture projects. But what really is hindering it, and we're seeing this a lot in the former Soviet Union states, there are geopolitical and economic relationships that are very difficult to transition at this time. And I was working on a project to bring carbon capture to Kazakhstan, and their problem was they were tied to coal resources for the Soviet Union, Russia. Okay, here's an example of how we've been able to improve existing facilities. This is from the Saskatchewan coal plant. It's a coal-fired plant, but they transformed this plant, modernized it to provide clean baseload electricity. And they reduced carbon dioxide emissions by up to 90%. They've captured over 1 million tons of CO2 per year, and they're using the CO2 for enhanced oil recovery in the Weyburn field. This is a great example of what we could do selectively. And I didn't include a slide here, but we could actually, let me go back. If we put CO2 on enough facilities, we can begin to be part of the solution of reducing the amount of CO2 in the atmosphere. The second one I want to address is natural gas. And this is a slide, this upper part is a diagram from the International Energy Agency about how do we meet the sustainable development scenarios of the future. And natural gas is needed to get us to the point that we can get off the most polluting and capture gas and burn with a lower footprint. And I always like this slide. I was in Australia. The natural gas is the perfect partner for renewable energy because it is dispatchable. So is it sustainable? You bet. It's a high power density. Facilities have a reasonable lifespan, but it's what really holds back nat gas from being a preferred energy source is that pipelines and emissions. These are the things that really society has drawn the line and wants us to do better. But they do understand the need for it. And I hear that in discussions that it pertains to quality of life, our ability to heat and cool and provide clean cooking water. And it is a transition fuel at this time. But can we do it better? You bet. We can upgrade existing infrastructures. It is a transportation fuel in terms of CNG. But right now, and I think we all understand this, it is a transportable fuel. Liquid natural gas is what is being shipped around the world to meet the energy needs that can't be met by local sources. And countries are relying on nat gas for security. Part of this talk would go into hydrogen, and we can maybe, again, we'll use that for a future talk. I want to show two examples of what we're doing globally for sustainable hydrocarbon development. Right now, we're working with the Oil and Gas Climate Initiative. This is a consortium of major petroleum companies, now energy companies, that have donated over $1 billion to finance projects to decrease emissions. And this is one example of monitoring methane emissions. There's a number of them out there. But the one I'm personally involved with is with my former alumni, Binghamton University, and that is locating orphaned oil and gas wells. And most people don't understand that across the US, across the world, the oil industry has roots back to the late 1800s, and small shallow wells were drilled and never plugged or capped, and they are emitting methane. If we can locate these efficiently, we can prioritize them to be plugged. And this is a project that's going on in southern New York. We're extending it into Pennsylvania, Ohio, to make maps of where these wells are, assign them the appropriate methane value, prioritize them, and get them plugged. I encourage you to look into this for South Dakota. Hydropower. Love South Dakota because you have a lot of hydropower resources, and this is your Big Bend Dam in South Dakota. The largest dam in the world is the Three Gorges Dam in China. And so is it sustainable? You bet. Power density is low, but the facility lifespan is high. Environmental use, we can talk about this and discuss it. Its land use is medium, but there is ecosystem disruption and population displacement, especially when you get outside of areas that are more regulated. Emissions are very low, but there are other, and you're much more versed, and this group is probably the right group to talk about what the riparian influences are upstream from all of these dams that we're creating. So social, and I really like this slide that's that Big Bend uses, because it does show that there is a recreation component, there is a tourism component. I'm a bit of a engineering geek. I like to look at different energy structures, and the amount of employment and maintenance, and importantly, the regulatory and scientific studies associated with this do provide meaningful work. So is it modern energy for all? Yes and no. It's regional. If you're in an area like South Dakota, great. If you're in an area like Arizona, limited. Existing infrastructure, most of our hydropower infrastructure has been put in over 50 years ago. But what we do love about it is it's both baseload and dispatchable energy, and it's needed right now to meet our electricity needs, especially in the US. But it is not a transportation fuel. It is not directly meeting our needs to move goods and services around the world. Wind. A very impressive amount of wind in South Dakota. It's accessible, affordable, reliable, and sustainable. Yes, it is. The power density is low. You get 1.8 watts per square meter generated electricity. But this is what really surprised me when I looked into this. The turbine lifespan is low, about 20 years, and maintenance is needed every 6 months. A number of the oil fields that I work on in Texas are associated both with pump jacks and windmills. And I was surprised to see the number of recompletions that are being done on windmills versus a number of times I have to work over a well. The environmental footprint is something that, for me personally, is something we need to look at. This photo on the bottom, I was flying across Kansas, and I was thinking, oh, look at that. That's the Mississippi lime play. And I thought these were all oil wells lined up, oil surface facilities. No, these are windmills in the heart of the United States. So this is just over Kansas. And then I took a look, I went out on Google Earth to look at South Dakota, and this is the Tatanka wind power footprint. And it still has it's got a footprint. There's over 59 wind turbines associated with this project, but it's a little subtler. And I do like that, there is some logic to it, but they are following roads on a pattern. And I'm curious to talk to people about what kind of wildlife migration patterns are helped or hindered by the roads that we're putting in to put in windmills. Let's see, let's go back down to emissions. Almost no emissions associated with it. But really the hidden cost of wind are the materials, manufacturing, and transport. The materials for wind come from all over the planet. They are assembled, a lot of it in Germany. They're transported to the US and installed. But the actual underlying materials are the same ones that we're seeing when we talk about battery storage, critical minerals and rare earth elements. And the other thing we're starting to see now is the first generation of turbines. We're seeing a landfill issue. So here's my plea. We need the best and brightest working on recycling and innovation. This is going on now. The resins and fiberglass that are used in these turbines, we're looking for different ways to make them into other products. And one of these are these pellets that can be made into particle board. So social, this comes out time and time again. People love or hate wind, and it's because they want individual or regional control of energy. And it does provide quite a bit of manufacturing and maintenance employment. But is it modern energy for all? And the answer to that is not yet. We still need better grid infrastructure, and we do need to work on storage options, large scale storage options to meet our energy needs. So I'll conclude this section with a brief discussion of bioenergy and ethanol. Accessible, affordable, reliable, baseload, yep. And these photos all come from South Dakota. It's a very interesting industry up there. It's economic, but the surface power density is low. So very, very large swaths of land have to be planted and harvested. And as I understand, the crop is 3 to 5 months, it's annual. In Northern Florida, we have several bioenergy plants, and we do it with pine trees, and we're in a 2 to 3 year growth cycle. But the environmental is land use intensity. Biodiesel, very high, biomass, a little bit lower, and ethanol from corn is the lowest. And I think when we look at that, it's not just the land use, it's the water use. And I have a slide for that in just a second. It does affect our agriculture, our industrial agriculture, and our farming. It's making farming monocultures. And there is some argument that we need to continue doing a diversity of farming activities to keep our ecosystems healthy. And the thing through the Nature Conservancy that I follow is decreased in forest and prairie biodiversity, not just in the US, but in other developing areas, developing countries. The loss of forest biodiversity is important. But for me, all that pales in comparison to the processing and storage and carbon dioxide degassing with making whatever product we're making. And it is end use of that product to where it's going. The emissions from co-firing are high and biomass a little bit lower, but when you're burning it, it adds back to the environment. So social, I'd say, great agricultural communities. My highest compliments to the South Dakota Prairie Coalition that has a calendar, an annual calendar. It just really shows the value of our agricultural communities. But the real reason bioenergy, and I'm talking more here about biomass to burn in form of pellets, is it meets the Paris Climate Accord criteria for renewables. That is what really has underlined the growth in this area. So is it modern energy for all? I don't know the answer to this question, but I have to ask it. If the CO2 sequestration benefits of plants are so high, is it better if biomass is left in the ground and unburned? That is a question for another, maybe for an adult beverage and discussion. So here's what I promised. When we look at water use, it doesn't surprise me, but it makes me concerned in a world that is having scarcer and scarcer water supplies. Fairly low, relatively low for ethanol and biodiesel, but there are several countries that are looking into these. Go back. When we look into biodiesel projects and doing algae, they have huge footprints and huge water footprints, not only in water use, but the amount of evaporation that's being taken out of the system. And that might be a focus for a future conference at South Dakota here. Let's talk about water use and bioenergy. I want to end on a happy note on this section with bioenergy. And that's something I'm seeing done in this northern area between these 5 states. Summit Carbon Solution is gathering CO2 from ethanol plants across this 5-state region. And it's an advanced state of development with the 7 plants that are in South Dakota. And somebody maybe can give me an update on this, that we're gathering the CO2 from making the ethanol, and we are going to sequester 1.6, maybe 1.7 million tons per annum of CO2. And it's going to be sequestered in North Dakota, and I suspect associated with some of the oil and gas fields up there. But we as a world produce 36 gigatons of CO2 annually, 36 gigatons. So if we're going to do something like that, even if they're 1 million ton per annum projects, we need 36,000 projects to get rid of CO2 if we just do sequestering. So I'd say We need a little bit from everyone, and this is an interesting and ambitious start. So I'm going to end on with a very short look. Let me check my time. Yes, I'm going to end with a very short look on energy in transition and uncertainties. And the other project we do here at Storm Energy is my husband and Storm Energy partner is an authorized agent for python removal from the Everglades. And pythons are an invasive species in the Everglades, and they have removed over 15,000 invasive Burmese pythons from the Everglades. So in conclusion of the energy picture, the first big energy scare of the green era, when I started giving this talk back in October, this issue of The Economist came out, is the energy shock. Really, what we learned about the testament to how much modern life depends on abundant energy. And that's when oil prices really started to vary in price. This is pre the Ukraine invasion. Our prices back then, petroleum prices were at $3, $4 a gallon. Blackouts were starting to roll in places around the world. And Britain had turned its coal-fired stations back on. That's a harsh reality. And this was said back in October. Europe was reminded that its supply of fuel relies on Russian goodwill. And we have seen that play out 6 months later. So it exposed deeper problems as the world shifts to a clean energy system, and that we don't have enough investment in renewals and transition fuels. There are rising geopolitical risks, and there are poor safety buffers in the power market. And I would add to this, the rate at which we're moving won't allow us to do this in the most scientific and sustainable way. And when I think about that, this slide shows me really energy realities. Everything on the left is data that we have on how we're using coal, gas, nuclear, biomass, hydro, wind, solar. And we see it increasing. As we know, our population is increasing. We're seeing the use of energy increasing. And some very smart people have made projections on what's going to happen. Everyone from OPEC to BP, the International Climate Change Commission, they're all projecting it's going to decrease. But this is the fourth thing you should take from this talk. Projections are not policy. We can will and wish something to happen, but until we regulate it and enforce it, and there's some very good talks today just on water about policies and regulations, this isn't going to happen. So we have to try and do with what we have to do better. And what we're seeing now is efficiency increase. This just came out in Forbes. Could a world in crisis propel us into a new era of energy? Yes, it can. They have found a way to link the Ukraine electricity system to the European electrical system faster than anybody thought possible. So I'm going to continue to follow that, and we should all be following that. If we can find efficiencies in a time of crisis, we can find efficiencies to solve our energy crisis. So in summary, the world continues to use more energy. That's not going away. And sustainable development is a framework to look at the life cycle development of energy. And all of us are needed to develop all types of energy so we have access to affordable, reliable, sustainable, and modern energy for all. And with that, I'll just say, please take a look at AAPG. We have divisions. I'd love to see South Dakota's water group join with our Division of Environmental Geoscientists and get more visibility about your programs. And there's 2 upcoming conferences you might be interested in, the Carbon Capture Conference and a Sustainable Development Competition. For any of the students listening, we need your best and brightest ideas on how you see sustainable development evolving. And with that, I'll take questions.
All right, Denise. Well, thank you so much. That was excellent. Do have a couple of questions. First, how high do you believe oil prices will rise per barrel in the short and long term?
That's
put you on the spot.
That's always my favorite question. If I could predict oil prices, I would be wealthy and I would have a new roof on my house. It's supply and demand. Oil prices are absolutely dependent on global use. What caused them to surge is not necessarily the invasion into Ukraine. But the fact that we have recovered as a global population from COVID faster, the COVID lockdowns faster than anyone thought possible. So that's what caused that initial spike going back in October, and it's been continuing as the world opens up and getting back to work. So will it go higher? I want to say there's always pressure when you get over 100. There's always pressure on it to not go higher. But that being said, if there's a disruption in the supply chain for the transportation of liquid hydrocarbons, the price can go, it can go much higher than we've ever seen. I personally believe it'll hover somewhere around 100. I know I want to believe that because it makes us imbalance in terms of the energy, all types of energy we develop and how we develop it with the lowest environmental footprint and with the most societal benefit. Because make no mistake, all those hydrocarbons that we use for energy are taxable, and it supports a lot of our government programs, including our military.
Thank you. I have a question. You brought up the Carbon Solutions Pipeline, and that is just getting started on the permitting process in South Dakota through our Public Utilities Commission. And you brought it up as, it can be a positive as we move forward. But what we're seeing in South Dakota and Iowa is significant public opposition to it. And I was just curious if you had a comment on that, sort of. It's spun as a very good and positive project, but the opposition is pretty vocal, maybe because it's pipeline related, not so much energy related, but I just thought I'd ask and see if you had a comment on that.
I do, and you nailed it. You say the word pipeline and you're evil. I would want to say, I want to start calling these as CO2 capture lines. And we have to ask everyone to do their part. And I think we're seeing a change in global opinion about what doing our part means. When you're watching a population in a country dealing with war, what does doing our part mean? It means giving a little to get a lot. And it means understanding that we can monitor these pipelines. We can monitor these pipelines better than we ever have before because we have the technology, the sensors and the drones to have 24/7 monitoring of pipelines out there. Are there going to be accidents? Of course. We have accidents on our highways. We have accidents in our homes. We have accidents in our businesses. But if we have an awareness and we monitor, we can improve what we do. So I think what's important is what we're all trying to do is communicate what those risks are and communicate not just the risk, but what are the benefits? And we need what you're doing. If you're going to have an economy based on bio products, then we really want to have a way to capture the CO2 from the biodiesel and ethanol that's burned. And that's doing our part. If you produce it, you should be responsible for it. And we're seeing energy companies are being held to the line. We produce petroleum, we need to come up with carbon capture. We produce biofuels, we need to come up with carbon capture. And there's more slides that I didn't show, but we're doing a lot of direct air capture is now growing. We can put those in oil fields and have a lower footprint because we can do that. But in terms of these very large footprint ethanol plants, you've got to have a collection system. So maybe we just call these infrastructure lines because infrastructure is a positive thing. So maybe what we need to do is get a group of us and go speak to these communities, have Q&As. And it needs to be people that can say, I don't have the answer, but let's talk about it.
Great, thank you for that. We're about out of time. I'm gonna ask one more question before we move on. Dealing with orphaned oil and gas wells. The question is, do you happen to have a kind of an idea or cost estimate of what it costs to cap those wells?
I do not for your state, but I can, if you email me, tell you what, I'm going to put my email in here quickly, or if I can, my contact information is with the organizers. If you contact me directly, we can get you. I want to say it can be as low as 10,000 if they're very shallow, and it can be as high as 100,000 if they're complex.
Right, and folks can certainly reach out to DANR, our minerals and mining program has an oil and gas program that deals with that and would have in-state numbers as well.
But I'd love to bring our drones out and fly an area and see how many we can identify. It's a great project for your students and state organizations to work on together. and high visibility.
Well, Denise, thank you so much. We appreciate you being with us today and learning about what you had to say. So thank you. All right, we're going to move right along. Our final presentation today comes to us from Dr. Christopher Schmit at SDSU. He will cover fundamentals of anaerobic digestion and its use as a resource to produce methane. Dr. Schmit currently serves as a faculty member at SDSU's Department of Civil and Environmental Engineering, as well as the Director of Water and Environmental Engineering Research Center. Dr. Schmidt's presentation will include basic anaerobic process microbiology, as well as biogas production and uses. He will also be covering information on anaerobic reactor types and how they differ in performance. Welcome, Dr. Schmit. Thank you for being here.
You guys hear me okay?
We can.
Which, are you seeing my PowerPoint presentation or my screen with double kind of pictures on it?
Yep, we are seeing your presentation slide. So I think, sir, you are good to go.
All right, good. I wasn't sure because I have two monitors and sharing can sometimes get a little confusing because you don't know exactly what you're sharing sometimes.
I've been there.
Okay, well, welcome everyone. I'm glad you had me invited me to talk. I'm really interested today in talking about anaerobic digester fundamentals with you. My goal for this presentation is to kind of get people up to speed with some of the just the basic things about anaerobic digestion that most people might not understand or have thought about. And hopefully with this information, you guys will be able to maybe have a better appreciation of how you can use anaerobic digestion you know, in treating industrial and agricultural wastes. You know, I started working on high rate anaerobic digestion as a graduate student way back in the early 1990s. So, you know, I was got my degree at Iowa State University. We were doing a lot of work. So done a lot of work with agricultural and industrial wastes and seen a lot of things over the last 20 plus years. Just to give you a little bit of idea of what I'm going to talk about, I'm going to talk a little bit about process microbiology. I don't want to get too in depth in that, but if we don't understand how the microbiology works in a digester, we might not understand appropriate uses and how much attention we need to pay to those digesters. I'll talk a little bit about biogas production, essentially what kind of energy we can expect from biogas. I want to talk a little bit about reactor types because I think just the fundamental knowledge of the different types of reactors that are out there and what they can do and what they can't do can be good for implementation and other things. And then just a little bit on odors, and then in my opinion, some of the barriers that I've seen over the years to implementation of this technology. So as you can see, they come in all shapes and sizes. Anaerobic digestion occurs in the environment all over the place, whether we like it or not. Here's a small system in China. They don't have to be big, and small farms can put these in, but just showing you some things that I've found over the years. A little bit on microbiology. To get the overview of what we do with anaerobic bacteria when we're trying to generate energy is we're converting organic matter, which is carbon matter, into new cells. The bacteria themselves want to grow. That's their main objective, is to take organic material, incorporate it into new cells and reproduce. And with that, we also get some energy in the form of heat. So these bacteria will produce a little bit of heat, but they also produce methane and carbon dioxide. The beauty of the anaerobic bacteria is because they can't use oxygen, oxygen is actually toxic to these bacteria. They produce methane instead of carbon dioxide. Actually, they produce methane and carbon dioxide, but the methane production is part of that biology. Whereas aerobic organisms produce carbon dioxide only. And because of the anaerobic bacteria can't use oxygen, this is a very low energy yielding reaction, to be quite honest with you. The anaerobic bacteria don't grow very fast. This has a lot of implications for actually operating a digester. When we look at anaerobic versus aerobic digesters or processes, anaerobic processes, the bacteria produce a lot less energy. They grow a lot slower. And you can see that because they're producing methane, which has a lot of energy left over. So you take that organic waste and you're left with methane, that's got energy left in it. When you're left with carbon dioxide, can't burn carbon dioxide very well, can you? It's actually used as a fire suppressant because it doesn't burn. So these bacteria, because they're not using oxygen, they don't fully oxidize organic matter and it goes to methane. If we look at a bacterial cell itself, we understand that these anaerobic bacteria are single-celled bacteria, and they take organic waste. They also need nutrients and minerals, just like any living organism, the main ones being phosphorus and nitrogen. And they produce more cells, reproducing, they produce methane, and then they produce some carbon dioxide. Now, it's not quite that simple when you look at anaerobic digestion. So here I have just a diagram of an anaerobic digester. In this case, we're going to feed that. We can feed it either manure, animal waste, or we can feed organic waste like a food waste or something like that. But what happens is there's not just one bacteria that goes from taking that manure and converting it to anaerobic bacteria. There's several bacteria that are operating on that waste, and they do it in a sequential manner. And that's super important because we have to make sure that all of the bacteria that are involved in the process are healthy and have an environment that they can thrive in and do their job. In this case, in this diagram, you can see that we have a left and a right on that digester, acid-forming bacteria and methane-forming bacteria. And my next slide, I'm going to break that down even more. But you can see in this case, if we have a manure or organic waste, it's a complex organic material. And then it gets broken down into more simple organics by one group of bacteria. And then another group of bacteria will break it up into acids. And another group of bacteria will take those acids and actually make methane. Those are the methanogenic bacteria, the final step in the process. And from a digester, you can get these various products. You can get biogas, of course, which is probably what we're going to be after. But we can also get this effluent, which is rich in nutrients, which we can put back onto the land to take those nutrients, that nitrogen and phosphorus, and recycle it back onto the land. And then you might even be able to pull some fiber out of the digester and reuse that as bedding. Oops. So if we look at a little bit closer at the microbiology that occurs within these digesters, so we're starting out with these complex organics. And where you start on this diagram depends on what waste you're putting into the digester. Clearly, if you're going to put in a soluble organic waste, that's going to be a lot easier to degrade than a insoluble organic waste. So, if we could put in sugar water, that would be the best. The bacteria can go to town. As a matter of fact, if we have sugar water, we can make hydrogen instead of methane if we choose to. But if we take these complex organics like proteins and polysaccharides and fats and oils, they are not readily degradable easily. A lot of these materials cannot pass through the cell wall into the anaerobic bacteria. Remember, anaerobic bacteria have they're single-celled, and everything that they sort of speak eat has to pass through the cell wall. So we have this whole phase one that has to occur with these complex organics called hydrolysis. And what hydrolysis is doing is it's taking these complex material that are maybe insoluble or can't pass through the cell wall, and it's solubilizing this material so it can get through the cell wall. This, if you have a complex organic material like a manure or some food waste, this can be your rate limiting step in your digester. Hydrolysis is the thing that limits your ability to make methane a lot of times. So paying attention to the hydrolysis phase can be quite important. But the first group of bacteria do break down the organic material into simpler things like sugars, amino acids, and peptides. And if you remember back to your maybe 8th grade biology, these proteins, which are made up of amino acids, those amino acids contain an amino group which has ammonia in it. So there's a lot of, if you have a lot of protein in your waste, your digester, you're going to produce a lot of ammonia. And that's because of the ammonia, that's the nitrogen that's associated with those proteins and those amino acids within those proteins. So we get this hydrolysis phase and it breaks everything down into simpler organics. And then we have another group of bacteria, which we call the acidogenesis phase. They're going to take these organics and break them down into volatile organic acids. Some longer chain, some shorter chain, but we're talking about propionic butyric acid. These chemicals actually are where a lot of our odors come from. Propionic acid is one of the main constituents of like sweat. Butyric acid, rotten butter. I mean, these things are rancid. And so these acids are what cause a lot of the odors, and we'll talk about that later in anaerobic digestion. And then we have another group of bacteria that are very much specialists, and these are the acetogenic bacteria. And their main role in the anaerobic digestion process is to convert these shorter chain or longer chain organic acids into acetic acid, which is basically vinegar, and acetic acid, and then we'll get some hydrogen in this step too. Okay, and so that's the acetogenesis phase. Then we have another group of bacteria which are also specialists. There's only a few dozen identified anaerobic bacteria that are able to convert acetic acid or hydrogen into methane. And so those are methanogenic bacteria. The methanogenic bacteria, that's the last phase. And so that represents the complete conversion of that organic material into an inorganic carbon, in this case, methane and some carbon dioxide. And so the methanogenic bacteria are by far the most, they're the hardest organisms to grow. They're the ones that have the most stress, and they're usually the first ones that you'll see stop growing or stop performing well. And so we'll see that a lot in anaerobic digesters. When we operate them, we'll see that a lot with a buildup of acids, a lowering of the pH. That's because what's happening in that case is your methanogenic bacteria aren't performing, and you're building up the acids from phases 2 and phases 3. And so once you build those acids up and your methanogenic bacteria aren't performing, then you start getting lower pHs, you start getting odors, and things start going south, as they say, in your digester. So these organisms all are kind of in a mutualistic society, so to speak. They perform mutualism. And if you have a buildup of acids, that starts causing all sorts of stress on the other organisms. So the methanogens have to be working well to keep the acids down and produce your methane. So these phases all have their own groups of organisms that are working together in consortium in that digester. And so that's one thing I think a lot of people sometimes don't understand, is that it's not just one bacteria that's doing this. There's a lot of bacteria that it's a chain, almost like a production line, where they're working on each organism relies on the previous organism to provide their food so that they can do what they do. If we look at the methanogens in a little bit more detail, they are very sensitive to a number of factors. I'm going to just point out a couple of them so that people maybe have a better understanding of why these are important. One is pH. So the methanogens operate at what we would call a fairly narrow pH range. So on the outside looking in, they're about 6.6 to 8.5 pHs where they are going to get their optimal growth. As you can see, this is a conceptual diagram of the activity of methanogenic bacteria with pH. And you can see that they have a very narrow range. You want to operate at the top of that curve, because that operates the maximum activity, and that's where you want to be operating. So they have a very narrow pH. As a matter of fact, you really want to be at 6.8 to 7.4, I would say, is where your optimal range is going to be for the methanogenic activity. Once you get outside that range, you can see the activity starts to drop. And if you get too far outside that range, the methanogenic bacteria just stop working altogether. In the industry, we sometimes call that a stuck digester. Your methanogens aren't working. They're not necessarily dead. They're just not able to process those organic acids into methane. So we can get them back. And a lot of times we'll lime our digester. We'll add, because a lot of times we'll see a low pH, we'll add lime or some other neutralization chemical like sodium hydroxide or something to get the pH back, to try to revive those methanogens and get their activity back up and going. So pH is really important to be monitoring in your digester. Other things we'll monitor, like the volatile acid to alkalinity ratio, because the alkalinity that's in your system can buffer against pH changes. And so that's another thing that we'll oftentimes monitor when we operate these digesters. Another super important thing to think about when we talk about anaerobic digestion, especially with animal wastes, is ammonia toxicity. And there's a couple things to understand about ammonia toxicity from a fundamental standpoint. And what's actually most toxic to the organisms, the methanogens, is actually NH3. And if you understand ammonia at all, it comes in two different forms in the environment: NH3, which is ammonia, and NH4, which is ammonium. And you can see that with that equilibrium reaction that I have listed there, that it is in equilibrium. So you can get either ammonium or ammonia, and they'll exist in both states. And you can see, because we have this H plus on the right side, the pH determines how much ammonia and how much ammonium you have. Okay, so the pK for this reaction is about 9. And what that means is that a pH of 9, it switches to primarily NH3. Below pH 9, it's mainly in the NH4 form. So NH4 is definitely where you want to be. It's less toxic than NH3. So what that actually means, though, in the long run for digesters, is ammonia is more toxic at higher pHs because you have more NH3 than NH4. in the main place that we're interested, or the main wastes that we're concerned about for ammonia, are anything that has protein in it. As I mentioned before, those proteins with those amino acids are going to have amino groups, are going to have every amino acid is going to have an NH2 attached to it. That's going to cleave off relatively early in the digestion process, because there's the bacterial produce enzymes that'll cleave that, aminases that'll cleave that NH2 off and put it into solution as ammonium or ammonia. So the higher the pH, the more toxic ammonia is going to be. And we see that in the most proteinaceous wastes, or the wastes that have the most proteins in, include swine waste and poultry waste. For animal waste, it depends on how efficient the animal is. And it happens that chickens and pigs are not very efficient eaters. So they have a lot of protein left in their waste. That can be good news because we can convert that to methane, but it can also mean that there can be a lot of ammonia that's introduced. So these wastes are particularly of concern to us, and any other industrial waste that you might be looking at for an anaerobic treatment. If it has a lot of protein in it, I'm thinking like processing, cattle processing, hog processing, those wastes can be a particular concern in terms of ammonia toxicity. In general, if we have 1,500 to 2,500 milligrams per liter of ammonia measured as nitrogen, we start to get very concerned about ammonia toxicity. The good news about this type of toxicity or inhibition is that it is reversible. We just have to find a way to either dilute out the ammonia concentration, which is typically what we might do, or if we operate long enough, these bacteria can become acclimated to ammonia too. So we found in the laboratory that if we run with high ammonia concentrations for a long period of time, they'll actually become acclimated. Another important concept for digesters is temperature. And so the main thing here we're looking at is if you understand anaerobic digestion, you know that we tend to run it using mesophilic or thermophilic temperatures. The reason we do that is because if you look at the activity, once again, this is a conceptual diagram, but if you look at the activity of anaerobic bacteria, you can see that there's different groups of bacteria. The middle one would be the mesophiles, the right one would be thermophiles. The important thing about this diagram is that if you swerve a little bit above or below their optimal growth rate, you can see a large decrease in activity. These bacteria do not want to be at 58 degrees Celsius or 53 degrees Celsius. They really want to be set at 55 or 35. The worst thing you can do for a digester is operate at 45 degrees Celsius. You're in no man's land in that digester. None of the bacteria are operating very well. So you have to have a good temperature control on your digester if you want to have high activity and be efficient in the process. I think a lot of times, a lot of people don't understand that temperature control is a super important item, especially if you want to have a high activity. So we want to be either mesophilic or thermophilic, and you can be at either one. They have their advantages and disadvantages, but be at one or the other if you want to have high activity in your digester, which will be more efficient, which means you can have a smaller digester. If you look at the thermophilic and the mesophilic bacteria, remember thermophilic's at 55C, which is about 130 F, and mesophilic's at 35C, which is about body temperature, so about 98 degrees Fahrenheit. You can see that the thermophilic bacteria, they at a higher temperature, they can remove organics faster because they have higher activity because they're at a higher temperature. And so those reactions are going to go faster for those bacteria. And thermophilic bacteria are also able to perform pathogen destruction. We prove that in the lab. Oftentimes when we get up to 55 degrees C, we can start destroying pathogens, which are disease-causing organisms. So thermophilic bacteria have those advantages. Some of their disadvantages is because they're high rate, they tend not to be as good at removing organics. So you get maybe a little bit less methane overall generation. And you also have just a naturally higher amount of volatile fatty acids. So those acids, because they don't have as good organic destruction, the volatile fatty acids tend to run higher, and you might have a few more odors, plus the higher temperature doesn't help that situation either. Mesophilic bacteria then are going to have a little bit higher organic removal, lower volatile fatty acids, but you're going to have a slightly bigger tank, and because you're getting that slow organic removal. So you can choose to operate at thermophilic or mesophilic if you're going to do temperature control. Both of them have their advantages. Go down one here. So a little bit about biogas. one of the things that I think a lot of people I've heard over the years when people talk about and they present their data on their digester is they present their biogas production, which is fine, but we have to understand that biogas itself is not necessarily an energy source. It's the methane in the biogas. And the amount of methane that's going to be in the biogas actually is a function of the solubility of the methane and the carbon dioxide gas in the vapor phase as opposed to the liquid phase. Okay, so what that means from practical standpoint is because of the difference in Henry's law coefficients for carbon dioxide and methane, the lower the temperature that you're operating your digester, the higher the percentage of methane you're going to have in your biogas. So if you're going to operate your digester at 35 C or mesophilic temperatures, you're going to have probably 65 to 70% methane in your biogas. If you operate at thermophilic temperatures, your methane percentage might be 45 or 50%. We've operated digesters at 20 or 15 degrees Celsius, and we've had 80% methane in our biogas. Now, the amount of methane that you generate has nothing to do with this biogas composition. The amount of methane you generated is solely a function of the amount of organics that are converted into methane gas. So a thermophilic reactor might have the same conversion rate, but will have more biogas than a mesophilic reactor, but it'll have the same amount of methane. It's just that the thermophilic biogas has a lower methane percentage. So when you see biogas numbers that are being presented to you, take that, be very careful about biogas. You really want to know how much methane is generated, not the biogas. So hopefully with that kind of, somebody's presenting you with biogas, they'll tell you the percent methane so you can do that calculation. So the methane composition depends on the temperature. Temperature obviously affects the solubility of gas, and the methane volume depends on the destruction of the organics, not on the biogas methane percentage or anything like that. You can also see that we do have primarily methane and carbon dioxide with small amounts of hydrogen sulfide would be the main gas that we see other than those two, and some ammonia, and we have some other things that are produced also. But H2S is one of the main ones because that can cause some big problems with corrosion and other things if you're going to use that biogas or that biogas, because it can be converted to sulfuric acid in an aerobic environment. Well, I like to put in these little things that I find out. Here's a couple home units if you're interested in making your own methane. So you can buy one of these things and put it into your backyard or into your garage or whatever, and make your own methane and make your own fertilizer. So going back to that concept of the biogas, once again, the amount of biogas is actually not that relevant to the energy. It's the amount of methane that's in the biogas that's relevant. For example, methane itself has 1,000 BTUs per cubic foot. That's its energy value. If you have 60% methane in your biogas, you're going to have 600 BTUs per cubic foot. If you have 50% methane in your biogas, you're going to have 500 BTUs per cubic foot. So you can see here that the energy value of the biogas depends on the percentage of methane, because those other gases aren't going to give you much energy. Obviously, carbon dioxide is not going to give you any. So just keep that in mind whenever you see biogas being reported, that it's really the energy value of that biogas depends on the methane percentage, which depends on the temperature at which that digester was operated at. So we know that organics are going to be the main item or the main constituent that's going to create or generate the methane, which is what we're after if we're looking for energy production and sustainable energy and things like that. So we look at the organics. The role of the organics is they provide the food for the bacteria, which is converted into methane. The organic carbon in the food is converted to the carbon in the methane. So as the usable food goes up, the potential for methane generation goes up. So the more food you give the digester, if the bacteria are able to handle it, the more methane you're going to get. So if you want to maximize your methane production, then you have to optimize your organic removal. We do that by providing the right pH, the right temperature, and all those other things that the bacteria are going to be the right amount of time in the reactor so that they can actually utilize in the organics. And so that's one thing I want you to take away as we think about this is optimizing organic removal optimizes methane. The other thing is, as we learned with those different phases, that hydrolysis phase, where we have to take that insoluble organic and solubilize it, is oftentimes a rate limiting step. And by the way, as a side note, it's easier to solubilize those organics or hydrolysis at higher temperatures. So thermophilic digesters also have an advantage of being able to have higher hydrolysis rates. But at the end of the day, soluble organics are easier to degrade than insoluble organics. So a soluble wastewater is much better or easier to perform digestion on than an insoluble, because you remove that hydrolysis step from the equation. A lot of times you'll see gas and performance of digesters based on volatile solids destruction, volatile solids removal. Just keep in mind that volatile solids are directly related to organics. Volatile solids are the way that we measure organics in the laboratory, or one way that we measure them. So in the volatile solids test, we separate the solids from the liquid, usually by evaporation for volatile solids. And then we take those evaporated, the solids that have not evaporated, and we put them at, we cook them at 550 degrees Fahrenheit. And whatever burns off, we say is volatile solids, which are mainly organic in nature. Okay, so the volatile solids are a way to measure organics. So higher volatile solids destruction means more organics destroyed, which means more methane produced. So if you want to think about volatile solids destruction in the same way as organics, the more you destroy, the more methane you're going to be able to produce. Another thing that I want to talk about in terms of digester fundamentals are nitrogen and phosphorus. We've already kind of looked at the role of nitrogen. Since the anaerobic digesters are a reducing environment, most of the nitrogen is going to be in ammonium or ammonia form. And the phosphorus will typically be in either the soluble or insoluble form as a phosphate. But both nitrogen and phosphorus are conserved in anaerobic digesters. That means that as much nitrogen as you put in, you're going to get the same amount of nitrogen out. You'll get it out in two different ways. Most of the nitrogen will come out in the liquid, in the supernatant, if you will, in the form of ammonia. And then you'll get some of the nitrogen, which is going to come out in the solids. So when the bacterial cells grow, every pound of new growth of bacterial cells, you get about 0.14 pounds of nitrogen as part of that bacterial cell. And that's because when a bacterial cell grows, it has to make proteins and enzymes, which are proteins, and they all contain nitrogen. Phosphorus is about 2 to 3% of cell by weight of phosphorus. So the phosphorus is mainly going to be soluble with a very little bit of an insoluble. Either way, the important part of this is that all that nitrogen and phosphorus that we put into the digester, when we take it out, if we can get it back on the land, we can make this pretty sustainable for nitrogen and phosphorus. That nitrogen and phosphorus back on the land can help us to grow more crops, which we can feed to the animals if we're looking at animal waste. And then that animal waste, that protein and stuff can be consumed. And once again, we can get it all back into the land. So that's kind of the goal with that N and P, is make sure that we understand that nitrogen and phosphorus is a resource. There are different ways to capture that. I'm not going to talk a lot about that, but there are different ways to capture that, because I'm running out of time, so we need to keep on moving. For biological methane potential, I just wanted to show you a few things that we're able to accomplish in the laboratory. So we can do biological methane potential. Here we can see this is a dairy waste, and we run tests in our lab, which tells you how much methane can be produced from a waste. So this is what the test would look like for a dairy waste. We have some supernatant and fiber from a separation process. This is one we ran on a grease interceptor, the amount of methane we produced over time. This kind of test helps us to understand how much methane we can get from a waste, which helps in planning and things like that. So I just wanted to show you guys that. I wanted to go through a few different reactor types so you can have a fundamental understanding of how reactors work. Here's some municipal anaerobic digesters. So this is the old school. This is what you'll see at municipalities if they're doing anaerobic digestion, and we've got some floating covers there. The two main things that I want you to know or understand about digester technologies is that there are low rate and high rate anaerobic digesters. And the difference between what we call low rate and a high rate is what we do with the solids. In a low rate digester, we don't recycle any of the solids back into the digester. So the amount of time the liquid spends in the tank is the same amount of time the bacteria spend in the tank. High rate systems, we take some of the solids that are coming out of the digester and recycle them back into the digester. Those solids are primarily by bacteria. And that way we've separated the amount of time the bacteria spend in the tank compared to the amount of time the liquid spends in the tank. High rate systems allow us to have a much smaller reactor, but get the same performance as a low rate system. But then you have to have some kind of solid separation device in order to selectively recycle bacteria. So when you see high rate, low rate digesters, that's what we're talking about, is that solid separation that must occur in order to recycle the solids back into the digester. So low rate systems, they have a longer hydraulic retention time, which means they have a larger tank volume, tend to have lower organic loading. They're easier to maintain because you don't have to worry about separating the bacteria out. And they may have a lower gas production because they may not get as good performance because you don't have as large a bacteria population operating on that waste. And then everything on the opposite side of that would be for high rate systems. So high rate systems are a more economical or more economic investment, but you can get a little more gas, and they might be, but they're a little more difficult to operate too. So you have to think about all those things. So the typical low rate digesters, there's two of them that we would normally, three of them, I guess, that we would normally see. The first one would be like what we call completely mixed reactor. You have a reactor with a stirrer in it. You put influid in it, you stir it, you let the methane get generated. You need about 10 to 30 days of detention time to have that happen. The hotter it is, the less time you need. And hopefully we heat this, and it's really easy to heat these with excess biogas because you have plenty of methane gets generated to heat these reactors with extra leftover. Historically, these were very popular. This is what you'd see in municipalities, conventional anaerobic digesters. What you'd see more on the ag side would be maybe a plug flow system. In a plug flow system, you don't completely mix the reactor. You put waste in one side, you allow it to move through the reactor, and it comes out on the other side, and hopefully during that time you've generated methane. The advantage of these is that they're a little more efficient, they're a little easier to operate, but if you have toxicity issues, you're not mixing the digester, so the toxicity doesn't get distributed, or the chemical that's being toxic doesn't get diluted out with the entire reactor content. So you can get toxicity issues with these types of systems. Here's a typical plug flow system installed in an agricultural application. And they can be simple as a concrete bunker with a cover on it. And you put waste in one side, take waste out at the other side. Obviously, we've all heard of covered anaerobic lagoons. This is a very, what I call low technology system, but they work quite well. They long detention times means they take up a lot of space, but if you put a cover on it, you can reduce your odors and capture some of the methane. These will typically be at least 20 feet deep, and they're not mixed or heated. They're just left as is. So easiest to operate, but probably the least efficient. Here's a swine lagoon. Some of the more high rate technologies that are out there. Here we have what we call the upflow anaerobic sludge blanket. Here we have a sludge bed, and the waste is going to actually go through the sludge bed and move up and then out of the reactor where the gas is captured at the top. In this case, we're capturing that sludge inside the reactor. We're not allowing it to escape. So we've separated the HRT from the SRT. Main takeaway here is instead of a 10 to 30 day hydraulic retention time, we might be able to get away with a 1 day, which means 1/10 or 1/30 the size. So it's a much smaller reactor. Downside of this is it can't handle solids. So you do this for soluble waste, and very proven for industrial waste as a system. Here's one of the upflow anaerobic sludge blankets. But once again, this is a high rate system, but it has to have some kind of solid separation mechanism. In this case, it has a sludge bed, and the sludge is not allowed to leave. So settling is the mechanism. The bacteria are settling to the bottom constantly, and so they can't leave the system. More newer is we have these new anaerobic systems called anaerobic membrane bioreactors. The solid separation mechanism in this is you put a membrane on the back side of it. The membrane rejects solids, and so the solids stay in the system and are recycled through that sludge recycle back into the system. So that's an anaerobic membrane bioreactor. Once again, solids like agricultural waste, so solids are probably going to have a problem in this because it's going to be hard to get the membrane operating properly unless you do some settling or something in the reactor itself, because trying to pull the liquid through the solids and through the membrane, it's going to take a lot of energy. Just a few things on odors. Just understand that anaerobic digestion does have associated odors, mainly from the ammonia and the hydrogen sulfide. But if it's not operating properly, you start building up organic acids and it can become really bad. And so that's why sludge pits and other things that aren't operated properly as digesters, or if you just have waste laying around, can have some really severe odors because of those intermediate compounds. When you start getting methane production, those intermediate compounds decrease and the odors decrease quite a bit. So once again, anaerobic digestion reduces odors in two ways: covered reactors and treating the waste to make sure you're not creating those intermediate compounds in the first place are two ways to reduce odors in anaerobic digestion. And you can see that, there's the farm in Nevada there, 78.5% reduction in odor from raw manure to digestate. Just by digesting it, you do get a reduction in odor if done properly. And then I'm going to end with just a few barriers to it in implementation. The first one is cost. Doing nothing is always cheaper than doing anything. So the cost is pretty significant for putting in a digester. There can be some recovery of cost for energy, but historically, the best bet has been for those systems that can use the energy internally. So if you can use the energy internally in your production or in your process, that's going to reduce your energy cost by whatever you're paying for energy. A great example is in Sioux Falls with John Morrell, which is now Smithfield, of course. Smithfield, they covered their anaerobic digesters and they used that gas to run a boiler just to make heat. And that's a very simple thing to do. And they save, several $100,000 a year in methane costs, natural gas costs, just by a direct offset. Okay, so if you're going to produce energy to put back into the system, then that's going to have a significant cost too, because you're going to have to either clean up the gas or run an engine generator to make electricity. Another limitation that I see is implementation. And by the way, the cost thing is going to have to be done with that's going to have to be done on the regulation side or subsidized or whatever we can do. And we already have some of that in place, but there has to be a reason to do it before you're going to put one in just to make energy. You have to have a market and those things in play. Operation of reactor is critical. This is definitely a limit to implementation. If you don't operate your reactor properly, it's not going to work properly, and then it gives a bad name to the process. And it does require some expertise and some training. And so a lot of the failures I've seen in anaerobic digesters is they're subsidized. Maybe they're put on somebody's site that's excited about the technology, but doesn't have the expertise to run the technology. And it takes some expertise and it takes attention. You can't just put a digester on an ag site and expect it to run without anybody paying attention to it. We have an anaerobic digester here in Brookings, and they actually hire a separate company to operate it because they have the knowledge to be able to operate that properly. So it's not an easy thing to operate by any stretch. These bacteria are just like any other living organism. It's like having a ranch or something else, running any type of animals. You have to pay attention to them and meet their needs. Maintenance has to be done routinely. And so a lot of times what'll happen is you'll put these in and the maintenance isn't done. And after a few years, the motors start to go out and then there's no money there to keep that maintained and stuff. And like I said before, any excess energy must be sold at a reasonable price. So there has to be buyback contracts and other things that are in place or installed. I've seen I've seen a shift to more plugging into the natural gas lines, where you clean the gas up and put it right into the natural gas line, as opposed to trying to go directly to energy and plug it back into the energy grid. Once again, your best bet is if you can use the methane in-house to directly offset your cost, you're going to be way ahead in that way. And the other thing for implementation is appropriate technology. This has been a huge barrier. Not all technologies are appropriate for all applications. And if there's not a good design engineer, there's no textbooks out there on how to design these. So if your design engineer doesn't have a good handle on the actual technology, it can be installed in inappropriate places, and then it's already going to be set up to not work. So that's another one. And then I mentioned that. And then lastly, the owner must see the digester as part of the entire system. And you have to operate your system with the facility in the mind. You can't have the digester as an add-on. It has to be part of the entire operation. And you have to think about your digester in all parts of your operation. What are you putting into that digester? If you start putting a bunch of sand into your digester, it's not going to work, because the sand's going to take up space in that digester and it's going to reduce its volume, so on and so forth. So those are some of the limitations. I know I'm a little bit over here, so I better quit and see if there's any questions.
Great. Thanks, Dr. Schmit. Are we seeing more of these digesters show up in South Dakota at some of our operations?
What's interesting, it's a cyclical process. We saw a big push for these in the 90s, and then in the 2000s we started to not see as many of these being put in. So I'm still seeing most applications are on the industrial side, where you can have the expertise in the volumes. We see some farm digesters, but it seems that there's a renewed interest in these once again. And so it just, a lot of it depends on energy prices, and is been where a lot of the barriers have been that I've seen over the years. So the big issue with ag digesters is they work great, you know, if you have the right operators and stuff like that, but then you have all this energy and methane and the producers don't know what to do with it. You know, it'd be nice if your facility was located next to an industry that needed natural gas, because then you'd have a natural fit there. But most of these ag producers, they're in, you know, they're out in the country and they don't have an easy way to transport their energy into the system. Obviously, Europe, because of their size and, you know, their politics, are way ahead of us in terms of implementing anaerobic digestion technology. They have a lot of, what I think could be more successful would be regional facilities. They do that a lot in Europe, where they'll have a regional facility. So you'll have a lot of producers or industries trucking their waste to one facility, and that facility is designed and built just to make energy with anaerobic digesters. And so then they can take all these different types of wastes, and if there's toxic issues, they can dilute them out with other wastes. I've seen some interest, like in Sioux Falls, with their upgrade. They're looking at increasing their anaerobic diet, because they do have engine generators there. So they're looking at putting a facility in for dumping. We've done some work with them so that, you know, that people can haul their waste to the facility and go right into the anaerobic digester. That grease interceptor data that I showed you is from a grease interceptor in Sioux Falls, from one of the large restaurants. And you can get quite a bit of fats, oils, and grease make great. And that's why the biodiesel people try to steal all that restaurant grease, because it's a great energy source. Really,
Excellent.
I mean, how do you store energy in a human being? You know, in fat. That's where the energy storage is. So anytime you get fats, oils, and greases, great energy production from those.
Well, excellent. Thank you for that. I don't see any other questions. So thank you so much for your time today. We really appreciate you being part of our conference. And with that, we have made it to the end of the 2022 Environmental Water Quality Conference. Thank you to all of our speakers for taking time out of your very busy schedules to participate. It's been great topics, good interaction, and we really are really grateful for your participation. At our peak, we had 90 folks online today, which is a great number. So glad we had solid interest. Just a couple of notes before I sign off. We will be sending out a survey to attendees to see how DANR and SDAP can make this conference better and you know, continue to evolve what it looks like, you know, moving into the future. Also, if you need those PDH forms, don't forget to email Brian Ferris at brian.ferris, that's F-A-R-I-S, at state.sd.us to get your PDH forms. And with that, we will close for the year and hope to see you all again next year. So everybody have a great day and take care.